Кость, как звук? 1, 2, 3, 4, 5. Ок. 3, 4, 5. 1, 2, 3.
Пленарный доклад в этом зале, если я правильно понимаю. Так ну еще вроде как 2 минуты. Значит, я понимаю, что в зале в основном присутствуют, так сказать, русскоязычные участники, но тем не менее программный комитет желает, так сказать, сохранить международный статус конференции. Принял то самое это решение, что доклады надо делать на английском языке. Поэтому я вступление тоже сделаю на английском языке. Ну, вроде пока еще на рубль, а доллар, так сказать, не вытеснил, наверное, это правильно. Но мы можем начинать. Let us start our work. Dear friends and colleagues, I am truly glad to greet you here in Moscow at the ALT22nd conference. This is the 29th conference of the series began in 1993. I can say that after many years, our conferences have not lost their importance. And now it is regular and significant forums for presentation of new results and discussion of new trends in laser physics and laser technology. These fields develop rapidly. The main topics of the ALT22nd conference are laser matter interaction, 74 papers, biophotonics, 49 papers, laser system and materials, 31 paper, laser diagnostics and spectroscopy, 31 paper, the terahertz photonics and optoelectronics, 25 papers. It is impossible to embrace the whole scope of research in laser physics, but new strands of research appear at the conference each year. As laser technologies progresses and become cheaper, they are applied widely and successfully in many branches of industry and research. And novel laser sources are being designed for specific application in various spheres. And laser processing and materials and industrial application of lasers are traditionally important and will be also discussed here. Biomedical applications of lasers become wider and much more important with every year. Currently, the methods of laser medical treatment are used in almost every clinics and hospital. There is no any need to prove that in our time lasers operate as the most versatile instrument in almost all industrial, branches and not only, but in scientific laboratories, hospitals and clinics, and even in our households. During the years, the ALT conferences were held in many countries. This time, after many years, it is held here in Moscow, the capital of the Russian Federation. In this connection, I would like to express my deep thanks to Moscow City Hall and personally to Sergei Sobyanin, the mayor of Moscow, for the financial support of our conference. I sincerely appreciate the assistance offered by all of our sponsors and the financial support provided by Prokhorov General Physics Institute. The conference organizing and program committee have done their best to make everything necessary for fruitful discussions during the plenary talks, exchange of ideas, presentation of results, and establishing new contacts. We sincerely hope that the conference will contribute to wider and more efficient cooperation between the researchers working in the field of application of laser and laser technology. In conclusion, as the editor-in-chief of the journal Physics of Wave Phenomena and the chairman of this conference, I would like to offer to publish the conference materials in this journal. The journal is published in English, and the editorial board may assure you in high quality transition of papers presented in Russian. Finally, I wish interesting work, fruitful discussions, and successes to all participants of the conference. Thank you. And now Professor Konov will be a short talk.
My name is Vitaly Konov. I'm the chair of the program committee, and it is my pleasure to welcome you all here in this personal building of Russian Academy of Sciences. And especially I'm happy that at last we meet together in the form of on-site regime. So at last we see each other. There were 2 years break of such conferences, which, to my opinion, was an awful period. First epidemic, then this year there was another difficult problem appeared. This problem is related to international relations and sanctions against Russia. And all this created a lot of problems to be solved. One of such problems was where to organize the meeting. Typically, before we organized it every year in different countries. This year, it was practically impossible to do it, and there was no other choice but to organize it in Russia, and in particular in Moscow. And in fact, it was good because only the first meeting of ALT was here. All others were abroad. So it is not really a big problem. Besides, thanks to our chair and thanks to the support of the Moscow government, we have special financial support for such a meeting, which was very important nowadays. Second is participants. As you understand, this year we have no participants from countries which we call the West. From the West, we have mostly participants from Russia, as it was expected, and normally for all our previous meetings, majority of participants were from Russia. But this year it was almost total majority, I would say. Still, we have some visitors from other countries, and we highly appreciate that they agreed to come to Moscow and to contribute to our meeting. I hope that their participation from other countries will grow, and maybe from other countries as well in the future. And because majority of Russians, there was a question of the language. Will it be Russian or will it be, as usual, English? Finally, the committees decided that it should be English. We keep pace, and also we should show respect to our guests. Not everybody of them can speak Russian, so for them it would be convenient to participate in such a meeting. And so this was solved. Now we are ready to work. I hope that the conference will be successful, that you will attend it and you will enjoy it, and especially you will enjoy communication with some people from other research centers in Moscow, from other cities, and from other countries as well. Now a few announcements. First, today we'll have a meeting of the program committee. It will be held in the room 1324, 1324, in this building at just after the last talk of sessions, about 6 o'clock. So please, all members of the program committee, go there to participate. And also, I apply to session chairs to be careful about timing. We have invited talks 20 minutes, oral talks 15 minutes. Please stop the speakers 2-3 minutes before the deadline, so that we could have time for questions, and so we could keep schedule well. And the last announcement is that we plan to organize the competition of the best presentations from young scientists. Those who for poster session, only for poster presentations. So those who want to participate, they should be registered at the registration desk. They should supply them with the data about you, and you will give a special mark to mark your talk, your presentation, and the best will be selected during the poster session on Wednesday, and we expect to have 3 winners. First winner will receive 20,000, second and third by 15,000 rubles. That is practically all I wanted to announce. I remind you that there is a canteen, restaurant on this floor, which you could use during the lunch break. And there will be coffee breaks in the winter garden, just nearby our hall. And you should be careful about in which place will be your session. In the program, each session, information on each session contains the place, room number 1, 2, or 3. And they are there is a special paper, one list of a paper, which describes you which number corresponds to which color of the hole. There are holes red, blue, and green, and you should select them properly. So, if there are no other questions, then thank you, and I wish you a good conference and good time. Thank you. And now, I think we can move to... Each morning, 3 days, Monday, Tuesday, and Wednesday, we'll have plenary talks. And today, our plenary speaker will be Professor Andrei Naumov from now he describes himself from Lebedev Institute, but he is also he belongs also to another institute. He is a well-known scientist in Russia, and he will present to you, I guess, a very interesting talk where he focused laser physics on nanotechnology, combined both of them, and I hope it will be very interesting for you.
Thank you very much. Thank you very much for kind
sorry. And
introduction.
Just recently, on the last session of Academy of Sciences, he was elected to the Academy of Sciences of Russia. So he is the youngest physicist in the Academy.
Thank you very much. Good morning, everybody. It's a great pleasure and honor for me to be here and to open this lecture. And of course, I'm happy to see a lot of friends here. So I hope for fruitful discussions and good work during this conference, which is actually one of the best laser conferences in the world. So many thanks to organizers, academician Sherbakov, academician Konov, for this kind of invitation. So I plan to speak about quickly growing field of science, modern field of science, single molecule spectroscopy and nanoscopy. So I try to see, okay, this laser pointer. So I present a few organizations: Institute for Spectroscopy of the Russian Academy of Science, and Lebedev Physical Institute, Troitsk branch, and also Chair of Theoretical Physics in the Moscow Pedagogical State University. And this is a few photographies from our laboratories where we work in Russia, in the Institute of Spectroscopy and the Moscow State Pedagogical University. So, and I plan my talk as following. First, I will speak about keystones of single molecule spectroscopy and optical nanoscopy, which is super resolution fluorescence microscopy. I will speak about main principles and show a few cutting edge topics. The main part of my talk, I plan to devote our results and our work, and I hope I will find some further collaboration with some of you, and I will be happy for fruitful discussions. Especially I will speak about cryogenic single molecule spectroscopy, about spectroscopy and nanoscopy of novel photoluminescence labels like semiconductor quantum dots, different nanoparticles, perovskite nanoparticles, and also about colored centers in diamonds, which is growing by different technique like CVD and HPHT. Very important direction of this research is three-dimensional nanoscopy, when we can localize single quantum emitter with nanometer accuracy in all 3 dimensions. And finally, some new direction for our group, and very actual, very topical. It's extreme effective spectrochemical analysis with SERS technology, surface enhancement, Raman scattering. Finally, I will conclude. And also, I would like to note that 2022 is year of anniversaries. I would like to dedicate my speech to a few very important persons in this field, especially Professor Shpo, Polsky and Professor Personov. You see some anniversaries of birthday, 130, 90, and also we have anniversary of Moscow State Pedagogical University, where Polsky and Personov work a long time ago. Also, we have 70 and 50 years anniversary of Polsky effect and laser side selective spectroscopy, so-called Personov effect. And finally, 100th birthday of Basov. It's very important point because lasers is the main instrument in our work in single molecule spectroscopy and optical nanoscopy. So, this is our story. You see quickly growing interest to the field of single molecule spectroscopy. You can find beautiful review paper in the international Russian translation journal Laboratory and Производство, Laboratory Производства, number 1st in 2020. It was written by Nobel Prize winner W.E. Murnau, and you can find this story in this very nice review paper. But as I told, this story started from Polsky and Personov Scientific School. It is site selective laser spectroscopy, and you see pioneer works. It was done in the board of 80s and 90s. You see two papers. First one from United States, W.E. Murnau and Lothar Kader. They measured absorption spectrum of single pentacene molecule in paraterphenyl crystal. You see very bad signal-to-noise ratio, but this group was happy to announce this absorption spectrum, and it cost Nobel Prize for this pioneer work. A few months later, Michel Arid, with his group, at that time he worked in France, in Bordeaux University, they measured fluorescence excitation spectrum. They tuned narrow band tunable laser and measured integral luminescence signal depending the laser excitation wavelengths. So this is analog of absorption spectrum, but you see much higher signal-to-noise ratio. And it was a real revolution in our field, and from that time people start to work in many laboratories over the whole world. First it was low temperature measurements, and people use single molecules as a very effective probe to study low temperature dynamics of disordered solids, polymers, glasses, and crystals. I will show some examples from our works. So it was 89 and 90, and then a few years later in ATH in Zurich, a group of Urs Wild, they started to work with usual luminescence spectrum from single molecule. It was stereolene molecule in some polymer matrix, and you see we can measure already usual electronic vibrational spectrum, so we can analyze this vibronic structure and understand what molecule we observe in our experiment. Very important step was done at the same time. It was 94th, first paper on single molecule imaging. When we used two-dimensional detector, it was Vidicon tube. It was not CCD matrix. It was Vidicon tube with some amplifier, and you see some spots which correspond to position of different molecules in thin film. It was starting of fluorescence nanoscopy. At the beginning of zeros, people start to work at room temperature, and we are going to life science. A lot of scientists from biology, medicine, and so on joined our community, and it was a real great step for applications in life science. Of course, it was necessary to work with some new luminescent labels, and it was semiconductor quantum dots as epitaxial, as colloidal quantum dots, and of course nano and micro diamonds with colored centers. First, it was epitaxial quantum dots luminescence. You see, some pioneer work was done by a group of one Nobel Prize winner, our citizen of Russia and Soviet Union, academician Alferov, and his group performed first measurements with measurement of luminescence of indi-arsenide epitaxial quantum dots in gallium arsenide matrix. And a few years later, people start to work with colloidal quantum dots, core shell quantum dots. And a few years later, you see pioneer works with luminescence of single defect centers in diamond. It was a group of Jörg Wrachtrup, Fedor Zheleska, and also our good friend, academician Sergei Kilin in Belarus. And you see some zero phonon line from single NV, nitrogen vacuum center in diamond. And also very important step to measure Raman spectrum from single molecule. It is very important in order to recognize chemical composition of our molecule, in order to recognize what certain molecule we observe. For this, we should measure Raman spectrum, but of course, we need strongly increased cross-section, because in comparison with fluorescence, we have very low signal-to-noise ratio, very low signal, so we need some special instruments to enhance this process. And it was done in '97. And finally, it's a very important step, it was done a few years ago, single ions in crystals. A few groups succeed with such measurements. It is very, very low fluorescent signal because we have a long lifetime of excited state, but still you see single praseodymium ion in some laser crystal, and people observe both luminescence image and also zero phonon line. So, and from this point, we now have instrument to understand luminescence of single ions in dielectric crystals. And what we have now, okay, 2014 Nobel Prize for W.A. Mörner and Eric Bessig and Stefan Hell for development of fluorescence nanoscopy. And what we have now, it's biophysics, single molecule cytometry, nanosensorics, nanoantennas, very important step, DNA decoding and luminescence of molecular nanomachines. And of course, the story goes to quantum optics because we have a beautiful instrument for constructing of non-classic light emitters. Also theranostics and integral photonics on chip technologies. How difficult to measure single molecule luminescent signal? First of all, we should work with extremely low homeopathic concentrations of molecules in some media, in condensed matter. We should work on the level of yoctomoles, 10 power minus 24. Of course, we should work with thin films, sometimes in cryogenics. By the way, the pioneer work from our friends, W.A. Mörner and Lothar Kader, it was done at cryogenic temperatures, 1.5 Kelvin. And you see, in order to obtain only one molecule in diffraction limited volume, they work with homogeneous line on the wing of inhomogeneous absorption spectrum. So, and it was only the proof that people work with only one molecule in diffraction limited volume. But still, you see, with typical molecule, which we use in single molecule experiment, Tyrrhenian molecule, we have emission count rate about 10 power 9 photons per second. It's a huge value. With typical detectors now, photomultiplier tube, avalanche photodiode, CCD, and of course electronic multiplication, CCD, it's very easy to measure such a flow of photons. But still, at the beginning, it was some quite difficult task. Of course, we need emitters with very high quantum yield, with a proper excited state lifetime. Of course, a very important parameter, a low intersystem crossing, transition to triplet state, also triplet state of matrix, and so on. We need extreme chemical purity of our substances, so this is a question to our friends from chemistry side. And of course, low matrix emission and scattering. If we speak about Raman scattering, we need strongly enhanced cross-section because actually we have very, very low cross-section, so we need to apply some special technique like tip enhancement Raman scattering or surface enhancement Raman scattering. Again, lasers. For each experiment, we need specially constructed laser systems. It can be continuous wave or pulse systems. It should be narrowband and preferable tunable laser in order to excite our molecule in certain wavelengths. Of course, optics. Microscope objectives with high numerical aperture, with low aberrations and so on, proper working distance. It can be dry or immersion objective. And sometimes we need to work at cryogenic temperature, and it's a very difficult engineering task. By the way, for people who think, especially young people who think about some innovation, it's a very good task to construct cryogenic micro-objective with proper optical quality. And there is only maybe 1 or 2 companies in the world who produce such kind of cryogenic micro-objective, and we need it. It's extremely topical task. Interference filter, some dichroic mirrors, we need proper spectral bands and quality and so on. As I told, the detectors with small dead time, with very low dark counts and proper read noise. And of course, especially task software and programming, because we need realize computer control of experiment, and of course image processing. And sometimes we need to work with millions or even billions of molecules. So we need to realize special programming instruments, some special software to recognize these images. Originally, it was done with special supercomputer facilities. For example, in IBM research laboratory or in TH Zurich. Now we can realize image processing on the usual laptop. But for this, of course, we need to construct special software. For example, very topical task is using of artificial intelligence. For example, some algorithm for machine learning and neural network. So it's again some topical task. By the way, as we see, last year we realized some papers that we can measure luminescence of single molecule even with usual amateur camera, which you can buy in Avito, AliExpress, and so on. It's usual amateur web camera, and we can use it to measure image of single molecule. So now we have beautiful instruments for this science. So it seems to me that I have a problem with battery. So you can switch the next slide. Could you please? Yes. So what is the main principle? So if we measure fluorescence image from point like light source, some model, mathematical model, we can solve the task of diffraction on the optical elements exactly. For example, if we consider image of ideal point light source, which emits the light in the 4p angle, image can be described by this point spread function, which is actually Airy function, and you see the main maximum can be precisely described by usual two-dimensional Gauss function. So you see these two lines, solid and dotted, and you see it's practically coincide. So it means that if we consider in experiment, this picture from usual experiment, single Tyrrhenian molecule in polymer film, we can we can approximate this image by two-dimensional Gauss, and now precision of determination of lateral coordinates of point light source depend mainly on the number of collected photons. And the typical value with usual instruments now the following. If we measure a few thousands of luminescence photons, we can reconstruct lateral coordinates with nanometer accuracy. And you can see even from one of our last experiments how precision of lateral coordinate determinations depend on the number of photons. You see about 2000 photons, and we are going to quantum dot core size. It's core shell quantum dots with emitting core cadmium-selene. So you see the size of core is about 4.2, and already with 2000 photons we can reconstruct coordinates with such accuracy comparable with size of core. Of course, if we consider, for example, emitting dipole, we should reconstruct much more complicated image. For example, here you see, depending the angle between orientation of dipole moment of our molecule, we will have different point spread function. And again, we have a problem of computer processing of this image, but still, when we analyze such images, we can reconstruct not only position, but also orientation of dipole of our molecule. For structural diagnostic, we should realize the technique for separated detection of numerous single molecule images. It was done by Professor Betzig, who did this in the middle of zeros, and he suggests to use additional laser in our luminescence microscope in order to switch on and switch off luminescence from different molecules in the field of view of our microscope. As a result, we can realize technique when at each moment, in each diffraction limited volume, we have only one luminescent molecules. Thus, we can measure series of CCD frames and then reconstruct coordinates by computer processing, keep all the coordinates in the computer memory, and then we can reconstruct the images just by rendering of all the positions of these probe molecules. Thus, we can do such kind of experiments. This is typical images from imaging of neuron of brain of mice. They are on the glass plate, and you see, with usual microscope, we are limited by diffraction. We cannot realize, for example, synapse structure. But if we measure all the probe molecules, all the label molecules, you see, we can obtain thin structure of our image. And, but for this, for example, here we have about 500,000 of label molecules. So we should recognize quick image processing, and then we do. By the way, sometimes this technique calls as a digital microscopy, because we cannot work with this luminescence microscopy without computer processing. A few words about Raman spectroscopy. Of course, very fruitful instrument is tip enhancement Raman spectroscopy. I would like to note a few teams, for example, company and TMDT, who produce excellent atomic force microscopes for this work. A group of Sergei Kharintsov in Kazan, group of Professor Milokhin, who work with this technique. For example, here you see, you can observe tip enhancement Raman scattering signal from single quantum dot on the glass substrate, and you can analyze intra and inter quantum dot processes. And this is some kind of culmination of this technique. It is a group of Professor Abkarian a few years ago. They map individual vibration inside of organic molecules. It's some kind of porphyrin molecule, and you see with very, very high accuracy, sub-nanometer accuracy, you can map even separate vibration inside of single molecule. And it was a real culmination of this technique. If we speak about usual spectrochemical analysis, we can use specially constructed colloids or metasurface for surface enhancement Raman scattering. And here again, I would like to note a few beautiful works from group of academician Kukushkin from Chernogolovka. By the way, it was best result of Russian Academy of Science in 2021 when they use SARS for recognition of SARS-CoV-2 COVID virus in order to realize this cost-effective and very cheap device for sensing of this virus. Some specially developed metasurface and so on. And a few directions on some cutting-edge topics. So it's about time. You see, of course, we need new type emitters, molecular nanomachines, quantum dots, color sensor in dielectrics. By the way, not only in diamond, it is a question of, for example, rare earth ions in crystals. Some hybrid emitters, metal, dielectric, semiconductor, organic and bio. And of course, we are going to new spectral range, for example, infrared. We need some new approach to exotic synthesis. For example, new chemistry for macromolecular devices and so on. Some biological approaches, and very important in some new direction, DNA origami. When people start to work with precise and extreme resolution placing of single molecule by using of DNA structures. Manipulation by emitter properties, its parcel effect, plasmon nanostructures, intermolecular interactions, and so on. For example, nanoantennas, and of course, fluorescence nanoscopy, three-dimensional, multicolor structure and dynamics. For example, here you see a visualization of single drug molecules which are going to inside of living cell. And this is one of the last paper from W.E. Mörner about processes of COVID virus inside of living cell. So it's just a few months ago. So, but now I start to quickly show a few our results. For people who are interested about works, I would like to show a few principal papers about different sites. Especially I would like to note our international journals, Physics Uspekhi, Bulletin of the Russian Academy of Science, Physics, and also quickly growing journal Photonics Russia. I welcome all the participants to publish papers there. So, but okay, first and one of the main field of our research, it was cryogenic single molecule spectroscopy, when at low temperature we can measure zero phonon line of single molecule inside of solid matrix, polymer or glass. And at low temperature, this zero phonon line is very, very narrow, but also very sensitive to local environment. Thus, for example, we can sense each quantum tunneling process in local surrounding. So if we measure repeatedly fluorescence excitation spectrum and analyze this time evolution, we can directly measure, for example, individual parameter of tunneling two-level systems. Of course, for this we need some powerful theories. It was developed by a lot of scientists. I would like to remember Professor Igor Asadko, who developed, for example, theory which describe temperature broadening of zero phonon line with also process of so-called spectral diffusion, and of course intensity of zero phonon line. So we have a lot of theories to describe these processes, and I would like to show how it happens in real experiment. For example, usual Tyrrhenian molecule in polymer film, you see at low temperature, about 4-5 Kelvin, we have very narrow zero phonon line, which is split between two positions. It means that we have interaction of electronic transition of single molecule with quickly jumping two-level system in our film. Then at temperature 7 Kelvin, we have activation of one more tunneling two-level system. Then we have increasing of jump rate, And of course, across along the whole temperature range, we have broadening and shift due to coupling with phonons, with localized phonons. So we can analyze temperature dependencies, and then we can estimate different processes. For example, together with group of academician Yulia Gorbunova, we study macromolecular complexes. For example, such a huge jumps can be associated with moving of heavy atom in this porphyrin molecules. So we can analyze the jumps and we can understand what happens with conformation of single molecule. Actually, when we measure images, you see, for example, process of tautomerization in such phthalocyanin molecule, we can directly measure by analyzing of images of this molecule. It was done by our friend Alfred Meixner in Tübingen University in Germany a few years ago. So, of course, we can analyze phonon dynamics. For example, we can directly, if we scan the laser excitation wavelengths in broad range, we can directly measure so-called phonon wing, phonon side band. Then we can reconstruct phonon dynamics in our polymer film. In particular, we can study phenomenon of so-called boson peak in our disordered solids. And also we can realize structural diagnostic because we have a very high value of ratio between inhomogeneous absorption band and homogeneous line width of single molecule. So we can just tune the laser excitation of laser excitation wavelengths, some narrowband laser. So, and when the laser is in the resonance with electronic transition, we have emission of luminescence. So then we can reconstruct coordinates of each molecule and also measure zero phonon line. So, of course, we can prove that we have deal with single molecule. For this, we should realize some correlation measurements. For example, we can measure correlation, second-order correlation function with continuous wave laser or with pulse laser. Then we have anti-bunching in the case of single molecule. Also, we can study blinking effect when our emitter goes to non-luminescent state. We can measure kinetics from single emitters. Also, we can observe spectral diffusion processes from different kind of quantum emitters. But also we can realize structural diagnostic. For example, here it's a thin film of orthodichlorobenzene matrix, and you see with such a cracked sample, we measure about 300,000 of single probe molecules. Then we can reconstruct structure of our thin film, but already with strongly sub-diffraction accuracy, because it depends on the accuracy of position determination, so we have nanometer accuracy for structural diagnostic. But what is important, for each molecule, we know fluorescence excitation spectrum. So we can realize spectral nanotomography. We can look on the subsite structure, for example, here, typical Spolsky matrix, frozen hexadecan with terylene molecules. We can analyze subsite structure of our fluorescence excitation spectrum. So, of course, we can expand this approach. Unfortunately, I have not much time to say many words about this, but actually we can measure dependencies of zero phonon line characteristics on the various parameters, power, temperature, external fields. Then we can analyze these dependencies with appropriate theories and find the material characteristics. Then we can map these characteristics and look for different correlations. Here I would like to remember name of Professor Sergei Feofilov, who discovered effect of dependence of excited state lifetime in doped laser crystal, depending on the refractive index of material. So, and this effect, so-called local field effect, it was described by many theoreticians. A lot of theories who describe this local field effect. But what is important, dependence of excited state lifetime on the refractive index allowed us when we measure T1, we can find effective value of refractive index. Thus, we obtain instrument for local refractive index probing. It was done by our friends abroad, and also we realized this in our system. It was a hexadecan film with Tyrian probe molecules. Thus, we have instrument for sub-micrometer refractometry of thin film that is very important for different applications. So, a few words about another luminescent lamps, colloidal quantum dots, color-centered diamonds, and perovskites. For example, here we speak about quantum dots composites. It was done with colloidal quantum dot with emitting core cadmium selenium. And here I would like to note that we have very powerful instrument if we use combined spectrum microscopy. For example, here we study this colloidal quantum dot ensemble with a few techniques. For example, electronic microscopy. We measure also luminescent spectra, and also we use low energy Raman spectroscopy with our friends from Novosibirsk, corresponding member of Russian Academy of Science, Nikolai Surovtsev from Institute of Automatic Spectrometry. He measured directly value of energy of local phonons in this quantum dot. And we measure this value by another technique. We measure temperature dependence of exciton energy and spectral width. Thus, we find the same value and we can compare. And this is a very powerful technique to understand processes inside of quantum dots. So, and of course, we should study intra processes. For example, effect of blinking when quantum dots can go to non-luminescent state. It's very rich physics, and we try to do this by measuring of this blinking trajectory and also spectral diffusion, and then compare with different theories. So, a few words about new emitters. It's color centers in diamond. Again, we can study process of inhomogeneous broadening, temperature dependencies, some cooperative effects. For example, a few years ago, 2 years ago, we discovered effect of superluminescence flashes from microdiamonds with germanium vacancy centers. It's very interesting from applications point of view, because you see we have enhancement of emission by orders. Then we can use this micro and nano diamonds for different imaging purposes. So, okay, again some combined techniques. Just this year we realized combined measurements with electronic microscopy and optical microscopy in order to understand what happens with different color centers in different places of our nano and micro diamonds. Perovskites. By the way, most of these results will be presented by my colleagues, for example, Alexander Tarasevich and some other people. So, and of course, we need three-dimensional technique, and it can be done. This is technique which was suggested by our friend, Nobel Prize winner W.M. Murnher. He tried to use adaptive optic elements. Then, if we use a specially developed phase mask, it was done by our friends from Samara branch of Lebedev Physical Institute, Professor Kotova. They calculated special phase mask, and we can transform usual point spread function to specially develop two lobes point spread function, so-called double helix point spread function. And you see angle of rotation of these two lobes image directly correspond to the depth of position of our emitter. So we can reconstruct third coordinates again with nanometer accuracy. So you see now we have full picture about position of our emitters inside of film, or even we can realize three-dimensional tracking to do microviscosimetry or rheology experiments. So, and final slide is about Ser's metasurface. Again, you can see some talks of our colleagues, Dr. Sergey Bedin. By the way, he have anniversary birthday just today. So my congratulations. And you can see some talk from our PhD student, Елизавета Kozhina, about enhancement of Raman scattering signal with specially developed surfaces. And you see extreme enhancement of Raman signal by value of 10 to the 6, 10 to the 7 times. So now we have instrument for spectrochemical analysis on the level of single molecule. And you see some different types of such kind of substrate. So, and of course, I would like to note our team from many institutions, Moscow State Pedagogical University, Moscow Institute of Physics and Technology, Lebedev Physical Institute, Crystallography and Photonics, Institute of Spectroscopy, Moscow State University, our friends from Yoshkar-Ola, Skoltech, and High Economic School. But I would like to especially know the name of Dr. Ivan Yeremchev, who is one of the leader of this single molecule and nanoscopy field of research. So, and many of these results which I shown was done by his hands. And of course we acknowledge all the foundations, and this is our good friends from University of Bayreuth in Germany, group of Professor Jürgen Köhler and group of Professor Lothar Kader, and of course all our collaborators from over the world. So, thank you very much for your attention, and I hope we can find some point for joint research and joint interest. So, thank you very much.
Thank you. Questions?
Thank you very much for your very interesting talk. I have some question about one of your last slide about the surface enhanced Raman. How do you control the so-called repeativity of the substrate you have, or it's not a matter?
This is very good question. And actually what we find just now, we have, you see, it's some kind of stochastic surface. Of course, it's random. And hotspot which we observe, they are distributed over the place randomly. So, and actually what we try to prove just now, and we have paper which is submitted just now in the journal, in order to obtain robust statistic and robust spectrum, we should realize mapping of Raman signal over whole surface. And then we should realize some statistical processing of this signal, and only after that we can obtain a robust spectrum in order to realize spectrochemical analysis. Because, of course, you see we have hotspot not everywhere, and especially in the case of random surface, it's very difficult to do. By the way, you can, as I told, you can see talks from our colleagues, from Dr. Bedin and from Елизавета Kozhina. They can discuss this question in more detail, how to obtain robust statistics from such kind of experiments.
Thank you. Thank you. We have time for 1-2 questions.
Andrei, about the first question, and what is the localization of measurements to use these statistics?
Okay, it's a good question. I think you mean if we have very low concentration. If we have very low concentration, especially with large molecules, it's question of averaging. So actually, of course, we need a lot of molecules in order to prove the presence of different substances on our surface. We need average. And concept of single molecule, it's question how to, when we have hot spot and very low concentration, we can obtain signal from single molecule which are located by different ways in relation to hot spot. Of course, we can obtain different spectra, especially in the case of large molecules. And this is question for fundamental research, which we try to do just now.
Okay, thank you. The last question.
Thank you very much. I'm wondering if you have any clues whether the molecules penetrate in the pores or stay on the surface, and how that would affect the enhancement.
It's again the same question. We should study this. Of course, there are different types of substrate. Actually, our molecule can be inside of pore. It depends on the type of surface. You see here, for example, we have not any pores. We have only some tips. So, but of course, it's possible to do some special surface with some kind of holes, and then our analyte can come to the depth of this hole. So.
Yes, thank you. So let's thank the speaker again for a very interesting talk, very informative. Now we have our first coffee break, and we're a little bit late, so let's get together at 5 minutes past 11 after coffee break here.
Так, а вы разобрались с тем, кто выступает
Здравствуйте, Иван. Да, сейчас, секундочку. Иван, подскажите, пожалуйста, слышите ли вы меня? Здравствуйте, Андрей. Подскажите ли, пожалуйста, слышите ли меня?
Здравствуйте.
Здравствуйте, Андрей. Отлично вас слышно и видно сейчас. Я попрошу вас на время выступления других участников отключить камеру и видео.
Иван, здравствуйте. А вы как-то имеете отношение к организаторам или...
Да, имеем.
Вы меня не слышите?
Я вас слышу.
Добрый день, подскажите, слышно меня?
Иван,
Да,
Андрей,
слышно.
я вас обоих слышу отлично.
Да, добрый день. Я, наверное, не сильное отношение к организаторам имею. Вот меня Валерий Викторович позвал выступить. Мне, кажется, записали меня в чейры, но не знаю, а никого нет, что ли, или что?
Подскажите,
не знаю,
пожалуйста.
только вы в зуме, и я, и микрофон вот с столом.
Ясно. Ну, я думаю, сейчас просто все вот только собираются же с перерыва, поэтому должны, наверное, подойти.
Ну если вы будете по чайрам, да, тогда, ну как, вы знаете,
Господи,
что
я прошу прощения.
Да,
Здравствуйте,
я могу.
Андрей, Иван, подскажите, слышно ли меня?
Да, добрый. Вот
Да,
теперь
да.
слышно. Да,
Отлично, я
теперь
прошу прощения. Смотрите, отлично то, что мы вас видим и слышим. Подскажите, пожалуйста, у вас будут ли какие-то презентации, вы будете раздавать изображения?
Естественно.
Да,
Да,
конечно.
конечно.
Давайте с вами сейчас проверим демонстрацию экрана, чтобы у нас все работало, и после сможем подключиться к конференции.
Хорошо. Мне можно нажимать или вы скомандуете?
Подождите одну секундочку,
Пробуйте,
пожалуйста,
наверное.
сейчас. Да. Все верно, да? Отлично. Благодарю вас. Андрей, давайте вместе начнем с вас. Пожалуйста, включите демонстрацию экрана.
Организатор отключил демонстрацию экрана участников. Вы мне должны разрешить ее.
Да, сейчас, минуту.
Пока нет. Да. Вот Валерий Викторович появился перед телевизором.
Попробуйте сейчас. Так, вам нужно будет запустить презентацию и включить полноэкранный режим.
Да, сейчас я делаю. Сейчас, секундочку. Видно?
Да, все, отлично, благодарю вас. Вы можете...
Видно?
Да,
Видно,
да.
слышно, да? Хорошо, тогда я жду ваших указаний, там, фамилии.
Если вам удобно, у нас есть в боковой панели чат. Я могу туда писать, и за минуту до вашего выступления я предупрежу вас, что вы скоро выйдете в эфир.
Хорошо, договорились.
Хорошо, благодарю.
Да.
Тогда прошу вас сейчас отключить камеру и микрофон.
Да, хорошо.
Спасибо. Иван, давайте, пожалуйста, теперь с вами проверим демонстрацию экрана.
Давайте.
Да, и тоже запустить, пожалуйста, полноэкранный режим.
Видно, да?
Да, все отлично.
Все.
Все отлично, благодарю вас. Тогда тоже, пожалуйста, проверяйте чат. В чат за минуту до вашего выступления я напишу и предупрежу вас.
Ladies and gentlemen, it's time to start our section, the section of biophotonics. For those who do not know me, I'm Alexander Priezha from Moscow State University, and together with Valery Tuchin, who will be our first speaker, we are co-chairs of this section of biophotonics. And today is the first day. Our section will include 7 sessions. 3 sessions today, 3 sessions tomorrow, and 1 session on Wednesday. And then there will be a joint poster session also, where our posters of our session will be presented as well. Well, it's my pleasure to welcome all of you. And certainly we have many difficulties to organize the conference, the session, and many people have problems to come to attend. Some of the presentations will be made in online regime, but the organizing committee says that everything works. There is good internet connection, so these papers will take place. Well, and let us start. I will announce two first papers, and then this session chair, Dr. Chernomyrdin, will continue chairing this session. So I'm happy to announce the first invited talk. It will be done by Valery Tuchin. I think there is nobody here who doesn't know Valery. He's an outstanding person in biophotonics, not only nationally, but also worldwide, internationally. And we are looking forward to hear a very interesting presentation. The floor is yours, Valery.
Thank you, Sasha. Good morning, everyone. Indeed, this is a great pleasure for me to be here in Moscow. And I would like to share our recent results on optical clearing. And mostly, this is some way to the in vivo applications of this technology. So this is an outline of my work and a bit about basics of tissue optical clearing, then some examples of applications which we received and described recently. And to remind you that I would like to say that tissues are turbid media with very high scattering, which is huge, about 100 up to 100 inverse centimeters. And also this is low absorption media for the visible light, for the near-infrared, but highly absorbing the shorter wavelengths in the ultraviolet and also in terahertz range, in infrared and terahertz range, far infrared and terahertz range. So the main mechanisms are the dehydration and the refractive index matching, or better to say refractive index matching due to impregnation of some media with higher refractive index into soft tissue. And also in the hard tissue, it's also permeative for any chemicals. So, and also dehydration. So refractive index matching and dehydration, and very often it's too difficult to separate these mechanisms. Also, some washing out the absorbers is also important because the scattering allows to or help absorption to reduce penetration depth as well. So you see here examples of optical clearing, for example, of cerebral membrane. It became more clear. And one of the recent results which we described in the book chapter, this is a very, very, very fresh book, Biomedical Photonics for Diabetes Research, and this is chapter 1, where we summarize optical and structural properties description of the biological tissues under simulated diabetes mellitus, and how we can use optical clearing technology to measure the diffusivity of these optical clearing agents, which are working as a probing agents for the diffusivity. So high diffusivity with for the normal tissue, and low diffusivity for the glycated tissue, which is one of the complications of diabetes mellitus. So this is for skin, and situation for myocardium. These measurements were done model in vivo, but we provide measurements for ex vivo tissues. And so we can predict low diffusivity in skin due to glycation and predict the low diffusivity with heart muscle. In future, it can be technology which allows one to measure the complications or the level of glycation of internal organs, not only heart muscle, but some other, like brain and some other tissues. So another project we are working out right now, this is how the electronic cigarette materials penetrates within the different tissues, and now it's in lung tissue indeed. And we are measuring the also diffusivity and efficiency of optical clearing, but the main goal of this study, using the OCT, for example, and spectrophotometry, to measure what is impact on the optical properties, that means structural properties of lung tissue after, here, for example, for rat tissue, for rat in vivo, about 14 days of vaping. These rats showing significantly change of the optical properties, and tissue became more clear. But indeed, more clear. It's we can use this like endoscopy, technology. But in that case, we are only showing that some structural changes happened with this tissue. So the same for also electronic cigarette liquids was studied here. This is simple measurements ex vivo using some samples from the rabbit lung in this case. This is typical collimated transmittance spectra. You see here Sarette band here and some other hemoglobin bands here. What is important for this cigarette electronic liquid, that they contains of the glycerol, about 70%, and 30% of the propylene glycol. You see here, this is refractive index of glycerol in the broad band of the wavelengths from 200 nanometers up to 600 nanometers and further. So it is very important for us to provide some refractive index matching using this agent. And this is the transmittance of the electronic liquid, and which is compound from the glycerol and propylene glycol. Indeed, not so high transmittance, but enough high in the ultraviolet, mostly due to propylene glycol spectrum. So you see here examples of the normal tissue after the clearing, and in this particular study we tried to introduce technology of step-by-step optical clearing. One step, then remove clearing agent, and another step to model some technology which can be used in future. So you see here results of these measurements, which are summarized. You see here the collimated transmittance. This is the time from 0 to 1 hour of application of this electronic cigarette liquid, and this is the wavelengths from 200 nanometers up to 1,000 nanometers, infrared, ultraviolet. And this is the one step of clearing. You see here huge change in collimated transmitters. Then they put some immersion, we put the sample in the saline for 8 minutes, for some minutes. And after that, we again, 8 minutes. Yeah, and then we again immerse it in the optical clearing agent. And you see here the differences. It's pretty good to see here that how absorption bands influence on the optical clearing efficiency and so on. And this graph showing the same picture but calculated in the efficiency of optical clearing, which is a ratio of the increase in the after first step, the washout of the optical clearing agent is allows to increase optical clearing, and the interpretation is very simple, because this is highly absorptive media, and therefore the washout of hemoglobin allows us to have, using saline, to increase optical clearing efficiency, and this is the second step. So also we check up this idea to make tissue more transparent in ultraviolet, which very important for application of different kinds of the optical technologies, like deep ultraviolet Raman and some others. Also for oral mucosa, we can provide very good ultraviolet transparent windows, one window here, another here, and this is very effective from 200 to 300, from 300 to 400 nanometers. Time dependence of this clearing allows us to estimate the diffusion coefficients of the, these electronic cigarette liquids, and you see here numbers. Indeed, this is some sum between the diffusion coefficients of glucose and propylene glucose, which are main components of this electronic liquid. So another example, which is a way to the multimodality, when we can use as optical clearing agents, used for contrasting of MRI and computer tomography, X-ray tomography. Yeah, so this is a list of the tested agents. This is Gadavist, Magnivist, Datarem, and Visipark. This is X-ray contrast, and these three are MRI contrast. So we have a good efficiency. We checked it using collimated transmitters, optical coherence tomography, and go forward. So you see here we applied for enhance the fluorescence output. So before optical clearing, this is in vivo measurements, and this is after optical clearing, using any agents, including MRI agents and so on. So this is technology and data, especially for Gadabuterol or Gadavist. And we have a good statistic. We can increase the contrast and penetration depth, and to have a more intense fluorescence from in-depth. And this is checked up for a few animals or system or groups of animals. This is very recently published results when we use not a topical application of clearing agent, but intravenous injection of the Gadabuterol, of the Gadavist, which is normally used in practice as medicine. And we correlate images of fluorescence image of tumor cells. You see here, before and after. And this is also MRI image, before and after. We have two enhancement contrast by one injection of the contrasting agent, which allows us to improve optical and MRI images. Another example also, very recent, we use this technology, use these agents like gadobuterol and compared with the glycerol efficiency. And we see pretty good enhancement of the optical clearing using these agents, and also measure the diffusion coefficients, which is very important, of the gadobuterol within the tissue. So we can provide very simple optical measurements to measure diffusion coefficients of MRI agents without any MRI big machine. So, and also we proved that this is if glycerol is a hyperosmotic agent, even if it is low concentrated, and the gadobuterol was specifically designed for no osmotic stress. And you see here very, very small variations of the thickness of the tissue after application of the of gadobuterol. So another example, and Irina Yanin is here. She was the first worker of this, or main worker of this project. And we did it together with the Olympus company. And we tested a lot of optical clearing agent and quantified measuring using the spatially resolved reflectance spectroscopy in vivo, measured the reduced scattering coefficient on the time, and you see here reduction of the scattering coefficient, and more, this is arrangement here, this is a red here, at red in vivo, we pick up this pad of fat and measure. You see here, before optical clearing, after optical clearing. Very, very, very well seen, any vessels and so on. And the motivation for this work is to provide some surgery, any kind of surgery, laser surgery or any other surgery. And you have, when you go by your instrument through the fat, and you know that all our important organs are have a surrounding like a fat. And so you have to go through fat, and you don't, even you see some cameras, you use some camera and so on, you didn't see vessels, big vessels. So if it will be preliminary cleared, after that you can see and avoid to puncture these vessels. So indeed we try to use the histology to understand what is impact of the clearing agent on the living tissue, because it's not ex vivo, this is really in vivo. And we see that this impact quite acceptable, quite acceptable.
Whatever, you have 2 minutes.
Yeah, I'm finishing, yeah. So another example for blood, and within the blood we are looking for the melanoma cells, and we have a good efficiency to count these melanoma cells within the blood when we try to optically clear it. Also, the last example which I would like to show you, this is some optical clearing of laser-induced tissue plasma, and we use this technology, LIPS technology, and due to better focusing, we have much improved signals from different elements and count them better. So, and also it can be applicable well for different photodynamic therapy, for example, and first papers are appearing now, and also for photo inactivation of germs using different technologies. So we published recently this handbook and about optical clearing, and it's 37 chapters here, and the last information all over the world about this technology. I would like to recommend this book. And in conclusion, I would like to say that for years we are working on optical clearing and see that it well applicable for real medical application technology if you use some optical or MRI or CT techniques. So I would like to thank all collaborators. I showed their papers, and you see here grants and our collaborators. And also I welcome you to Sarat Fall Meeting, which will be this September. So thank you for your attention.
Thank you very much for a very interesting and informative lecture. We have time just for 2 short questions and short answers. Yes, please.
Thank you very much. Very interesting talk. I have a simple question. Actually, different tissues have different properties. So, how you understand for optical clearing, you should have a little bit different conditions. For example, time of processing and so on. Do you need some preliminary experiment in order to understand how to work with certain tissue?
Yeah, absolutely good question. So indeed, we have to study first the optical properties, structural properties. It's well documented, a lot of our works and some other works available. And after that, indeed, this is a main tool. So this is cellulose made from cells and some connective tissue. So, and it's more or less, it's everywhere in our body. So indeed, it's, we take it into account. Yeah.
Thank you. Thank you.
Thank you very much. I would like to ask another very short question, Valery. Your results show, and you said that optical clearing can be used in medicine. The question is, are the optical clearing agents already certified for clinical applications and approved, or it is just still experimental job?
So for years, one chemical like very diluted glycerol solution for many years already used in the ophthalmology to make clear cornea when it is turbid, to provide some surgery and so. But it's the only one that I know. We study, why we study the electronic cigarette liquids? Because this is a good composition of glycerol, very pure glycerol, and propylene glycol, very pure. It's certified for smoking, yeah? Not smoking, but vaping. And therefore, they approved by FDA and some other agencies. And therefore, I think this is a way to use it in medicine. For a lung, you can use it immediately, for example. And for other tissues, it also can be used.
So you can, but you may.
You may. I may.
Formally. You won't
formally. Yeah, formally, I think we may.
Okay, thank you very much. Unfortunately, with the time limit, we have to proceed. Thank you very much. Let's thank the speaker again. And let me announce the next speaker, who is Nikita Chernomyrdin from Prokhorov General Physics Institute and Bauman Moscow State Technical University. And his invited talk is entitled Terahertz Solid Immersion Microscopy, Review and Perspectives. The floor is yours.
Thank you for introduction. So here is the outline of my talk. At first I will tell about the applications of terahertz radiations in biophotonics. Then I will say about the problem of low spatial resolution. I will briefly discuss the solid immersion effect, and I will tell about particularly terahertz solid immersion microscopy, and I will touch such topics as terahertz wave scattering in biological tissues and the perspectives of terahertz solid immersion microscopy. As you might know, terahertz technologies have numerous applications in biophotonics and particularly in medical diagnosis due to unique properties of terahertz radiation. Among them, non-ionizing nature, an ability to interact with vibrational and rotational energy levels of molecules, and a strong absorption by water molecules. The latter strongly limits the depth of investigation of biological tissues, but it also serves as an endogenous marker for medical diagnosis. Such methods as terahertz imaging, spectroscopy, reflectometry, and others were applied for in oncodiagnosis, testing of tissue glycation and diabetes mellitus, estimating of transdermal drug delivery, and others. While all of these approaches mostly rely on water tissue as an endogenous label of pathological process. Here is, as an example, I show application of terahertz spectroscopy and imaging for skin cancer diagnosis and breast cancer diagnosis. Could you please do the next slide? Thank you. However, some problems are inherent to terahertz technologies, and low spatial resolution is one of them. It is one of the most important of problems. Here I show scales of some tissue inhomogeneities, structural elements, which scales are divided by terahertz wavelength 300 microns. As we can see, many of the tissue structural elements features wavelength scales. Here the red line is upper diffraction limit. But usually for describing terahertz properties, models with averaged efficient optical properties are used. They do not consider scattering of terahertz waves on individual tissue elements. But since many of tissue elements have subwavelength scales, some new approaches for describing of interaction terahertz tissues with wavelengths should be used. And also low spatial resolution strongly limits the accuracy of tumor margins detection. Nowadays, several attempts were made to solve this problem, among them wide aperture aspherical optics, terahertz digital holography, photonic jets, and others. But the highest spatial resolution was obtained using near-field scanning probe microscopy based on subwavelength apertures, resolution up to 0.1 wavelengths, and based on subwavelength probes, resolution up to 10 to the minus third power wavelengths. However, these approaches suffer from low energy efficiency. They require applying high power terahertz sources, sensitive detectors, and they require rather small distance between the object and the probe, so they interact and even damage each other. Another perspective approach which was proposed by our group for improvement of spatial resolution of terahertz imaging, is based on solid immersion effect. Here is this approach allows to improve spatial resolution by focusing electromagnetic beam on a small distance about wavelength behind the solid immersion lens made of high refractive index material. Here is the classical scheme of solid immersion lens. It is when the focusing beam, the wave front of focusing beam is concentric to the spherical surface of the solid immersion lens. Nowadays, solid immersion effect was first introduced in 1990, and since then several configurations of this method were proposed. Here is the super solid immersion lens, or it also called Weierstrass lens, diffractive solid immersion lens, angular aperture. Figures D and E show microscopy of microfabricated solid immersion lens for middle infrared and the visible regions. And here is the microscopy of planar parabolic solid immersion mirror coupled to planar waveguide. And here's a registered intensity distribution. And the last picture is a metamaterial-based solid immersion lens and its application for imaging of micro-patterned wafer and Blu-ray disc. All these approaches were applied in visible and infrared regions. Due to high spatial resolution, up to 0.15 wavelengths, and high energy efficiency, terahertz or just solid immersion microscopy have found applications in different fields. Here's its application for photolithography, thermal imaging, optical data storage, photoluminescence spectroscopy and imaging, Raman microscopy, non-destructive evaluation of microelectronic circuits and individual electronic elements, and fluorescence microscopy. And our group, for the first time, realized solid immersion effect in terahertz frequency range. We used high resistivity silicon as a material of solid immersion lens due to high refractive index in terahertz range, about 3.4, and low terahertz wave absorption. Here's the scheme of the developed solid immersion lens. It comprises two parts: a rigidly fixed hyperhemispherical lens and a movable plane window. Such configuration allows to visualize amorphous biological objects and soft tissues. There is such a feature of a solid immersion effect when the focusing beam is split into two parts. The low aperture parts undergo ordinary Fresnel reflection on the interface between the silicon and the object, and the high aperture parts undergo total internal reflection with excitation of evanescent waves. Interference of these two beam parts on the interface results in improvement of spatial resolution. And numerical simulations using finite difference time domain method have shown 0.16 wavelength resolution of this system. Here's the the scheme of experimental setup of terahertz microscope based on solid immersion lens discussed above. It is based on a backward wave oscillator as a continuous wave terahertz source and Galilei cell as a broadband detector. Terahertz images were registered by raster scanning the object surface by linear mechanical translators. We studied experimentally spatial resolution of this microscope and have shown 0.14 wavelengths and 0.15 wavelengths resolution in two orthogonal directions. We also applied terahertz solid immersion microscope to study different types of biological tissues. Here is the application of solid immersion microscope for studying fibrous breast tissue ex vivo. Here's digital photo, terahertz image, and histological image. We could visualize subvalent features of this tissue, such as single spherical fat cells and their agglomerates, which is pretty good for terahertz region. However, in previous applications of solid immersion effect in visible and infrared regions, only qualitative imaging was implemented with registration only intensity or amplitude of electromagnetic wave. In our work, we propose an approach for quantitative terahertz imaging based on solid immersion microscopy data. In this approach, we estimate refractive index of the object as a minimization of the error function between which is presented as a discrepancy between experimental data and theoretical model. In this model, we use air as a reference medium with a priori known optical properties. Theoretical model describing electromagnetic wave reflection from the object and the optical system is Based on Fresnel formulas, it considers wave polarization and the impact of ordinary reflected and evanescent waves. We verified this model using a finite element method, and in order to verify our approach experimentally, we studied a set of test objects with a priori known optical properties of some terahertz materials. First, we considered lowly absorbing media with absorption coefficient lower than 10 inverse centimeters in terahertz range. Here are terahertz images and refractive index distributions. We compared estimated refractive indexes of these objects and previously known values, and conclude that this approach works well for low absorbing media and can be applied in such fields as terahertz material sciences, non-destructive testing of dielectric media, as well as chemistry or pharmacology. Next, we considered highly absorbing media, for which some a priori knowledge about the absorption coefficient should be used. We also proposed an approach for estimating of water content in tissues based on estimated refractive index distributions. As a test system for verifying this approach, we used propylene glycol and its aqueous solutions. Optical properties of propylene glycol and its solutions were previously measured using terahertz pulse spectroscopy, and on this figure we compare estimated refractive indexes of propylene glycol and measured by solid immersion microscopy and terahertz pulse spectroscopy, and we can see a good agreement of this method. And also to demonstrate practical application of this method, we studied freshly excised intact brains and brain glioma from rats. Here is digital photos, terahertz images, refractive index distributions, absorption coefficient, and water content. And the last column is a histological expert. From these results, we could note that our approach allows to differentiate subwavelength features of brain tissue, and it is rather sensitive to small variations of refractive index, which could be useful in medical diagnosis. Also, I would like to touch this topic about terahertz wave scattering in tissues. Usually, efficient medium approach is used to describe scattering terahertz wave tissue interactions. It considers biological tissue as spatially homogeneous medium with efficient average optical properties. However, a lot of biological tissues have structural elements with dimensions comparable to terahertz wavelengths. As an example, here is the previously discussed image of fibrous breast tissue and our microscope allowed to visualize single fat cells and their agglomerates with dimensions of about 50 to 150 micrometers. For such types of tissues, where dimensions of structural elements are no longer negligibly small particles compared to terahertz wavelengths, knee scattering effects would take place, and thus it is necessary to develop some novel approaches for describing terahertz wave tissue interactions which would take into account structural properties of tissues. In order to demonstrate it, we calculated knee scattering parameters of model single spherical fat cell surrounded by homogeneous fibrous tissue. We could note that depending on the ratio between the particle diameter and the wavelength of terahertz radiation, we could expect strong forward or backward scattering as well as diffuse scattering of incident radiation. So we could conclude that it is necessary to develop novel approaches for describing this scattering. And also I would like to point some vectors for further improvement of solid immersion technologies. Since spatial resolution of solid immersion microscopy depends on the refractive index of solid immersion lens, it could be further improved by applying new materials. Here is the pilot simulations of solid immersion lens made of rutile. It is a material with high refractive index in terahertz range, about 9 to 11. We found out that such solid immersion lens provides spatial resolution up to 0.1 wavelengths, and we could note an interesting effect that such lens is almost insensitive to variations of refractive index, but it is sensitive to variations of absorption coefficient for highly absorbing media, which can be useful in medical diagnosis. And here is another configuration. It is a solid immersion lens made, this composite solid immersion lens made of hot pressed rutile and polypropylene powder. We found that such composite material features refractive index of about 4, and composite solid immersion lens provide resolution up to 0.2 wavelength. The advantage of applying composite materials is an ability to vary its optical properties by varying concentrations of rutile and polypropylene. But in order to minimize losses, it is better to use these materials in low frequency range. Thank you for your attention. Here is our research group, and collaborations are shown.
Thank you very much. So we have time for a few questions. Peter, please, your question.
Thank you for your talk, and if I understood you in the right way, that the best spatial resolution for terahertz can be achieved for near-field scanning microscopy. So what is the observable limit of spatial resolution compared to solid immersion microscopy? Because for solid immersion it's about 0.2 wavelengths, so what is the range of spatial resolutions for this near-field scanning microscopy?
Thank you. This is a good question, because when we came into this field, in visible and infrared regions, the highest achieved resolution was 0.15 wavelengths, and we thought that this is some limit of this method. And at first we obtained 0.15 resolution in our terahertz microscope as well, but applying rutile lens, we obtained resolution up to 0.1 wavelengths. We assumed that resolution in this method is defined by the refractive index of the solid immersion lens, so it's about the resolution of focusing system, which is before the solid immersion lens, divided by the refractive index. But for this system, it was expected about 500 wavelengths, but there was some limit about 0.1 wavelength. So this is interesting effect which we should study. What is the dependence of this limit?
Okay, thank you.
Other questions, please? No, no questions. Then let us thank the speaker again, and I will announce the next talk, and then we'll pass on the chairing to Dr. Chernomyrtin. So the next talk will be presented by Dr. Olga Cherkasova, also with co-authors. They are from the Institute of Laser Physics of Siberian branch of Russian Academy of Science in Novosibirsk, and the Research Center Crystallography and Photonics in Moscow region, Russia. Olga, the floor is yours. This is an invited talk.
Dear colleagues, so first of all I would like to thank organizing committee for inviting me to this conference. The topic of my report you can see, and this work was carried out by a large team from different institutes and universities from Moscow to Shanghai. This is structure of my report. I will see. I will speak about glioma and glioma biomarkers, about our experiments with the experimental model of glioma U87, about spectroscopy method, terahertz and infrared spectroscopy, which differ and complicated to each other on characteristic of spectral information, and application of this spectroscopic method with machine learning allow to analyze glioblastoma more carefully, and at the end of my report I give some conclusion. The most common brain tumors are gliomas, which begin in the glial supportive tissue, and glioblastoma multiforme is among the most deadly neoplasms. One reason for the poor outcome of glioblastoma may be delayed diagnosis and treatment, but knowledge about the early stage of glioblastoma is limited. The determination of biomolecules in body fluids has great potential for the early diagnosis of glioblastoma and non-invasive or minimally invasive control of treatment. Conventional molecular marker detection methods such as nuclear magnetic resonance spectroscopy, chromatography and mass spectrometry are complicated and time-consuming, and therefore the development of new non-invasive methods for early glioma diagnosis is urgently needed. Glioma biomarkers can be divided into circulating tumor cells, exosomes, circulating tumor nucleic acids, protein, and metabolites. This molecules can be found in different body fluids, and we are focusing on glioma biomarkers detection in blood using terahertz, infrared spectroscopy, and machine learning. This is a scheme of our research. We analyze brain tumor by magnetic resonance spectroscopy in vivo, and then we analyze blood plasma by terahertz spectroscopy and infrared spectroscopy during glioma development, and using machine learning method to create model for early glioblastoma diagnosis. This is our experiment. The glioma of orthotopic xenotransplantation of the U87 human glioblastoma cells into immunodeficit animals was used. The cell suspension was introduced in the subcortical brain structures through a hole in the animal's cranium, and the dynamics of the tumor growth was studied by means of magnetic resonance imaging on ultra-high field tomograph. And in this picture you can see the tumor volume, and you can see that significant tumor growth can observe from 14 to 21 days after tumor cell inoculation. We use magnetic resonance spectroscopy to analyze metabolites in brain cortex. In this picture you can see vortex position during magnetic resonance spectroscopy. injection site and control site, and we analyze these metabolites. And in the dynamics of tumor development, there is changes in the aminobutyric acid, glutamine, mionazitol, acetyl and taurine. And in this picture you can see concentration of mionazitol and taurine on the average stage of our experiments. And we use machine learning method to analyze magnetic resonance spectroscopy data. We use principal component analysis for feature extraction, loading analysis, and informative feature selection. This is different important metabolites, predictive model creation, and we obtain that it is possible to accurately determine the presence of glioma even in the early stage of the disease. The most informative biomarkers are taurine and acetyl aspartate, glutamic acid, mionazitol, and lactate. And then we use trigger spectroscopy for analyze blood plasma. Trigger spectroscopy, unique instrument that can be used for label-free diagnosis of malignancies because changes in the relative proportions of free and bound water and the relaxation time of either of these states can all be observed in the trigger's range. And this is our time domain spectrometer. We use in transmission scheme, and this is our QVET. Сам собой. Next slide. Thank you. Distinctive features of this method is possibility measuring directly refractive index and absorption coefficient, and possible to obtain dielectric function of sample during one measurement. And this is our experimental result. You can see trigger's absorption spectra, water, blood plasma of control or healthy animals, and blood plasma animals after 7 and 21 days after injection of tumor cells, and we analyze spectroscopic data with compare experimental data with dielectric function of water. You can see two-component Debye model and Lorentz term, and this is spectra of imaginary and real parts of permittivity, and we analyze first Debye term and obtain that during tumor development amplitude of first Debye term is diminished, but relaxation time is increased, and this data allow to speak that with the tumor development the amount of bound water in the plasma increases. Then we analyze trigger spectroscopy data with machine learning. We used as a first step trigger spectra preprocessing and feature extraction. We use signal smoothing by Sovietsky Galay methods, outlier removal by isolation forest. You can see principal component analysis. The second step, predictive model construction, validation, and informative feature selection. At the last step, we estimate relationship between tumor size and specific frequencies. And in this picture, you can see relationship between tumor size and triggered spectra of the studied samples, and informative frequencies are 0.19 and 1.9 terahertz. Next step was infrared spectroscopy. We work in attenuated total reflection mode, and In this picture you can see a spectrum of human blood plasma and spectral regions that correspond to known biomolecules. Analyzing absorption peaks, we can recognize vibration modes of specific substances and identify biomarkers molecules. And also infrared spectroscopy can effectively identify biomolecules, cancer biomolecules. And this is our experimental setup. We use only 5 microliters of blood plasma, and also we use machine learning methods for analyze spectroscopic data. And in this picture you can see our data, our results. So this is average spectra of mouse blood plasma during glioblastoma development on different stage, and this is pre-processing data, informative feature selection, and you can see support vector machine loading, and more informative. We obtain more informative infrared features, and this feature is image 1, image 2, and C ostrich bands. And in conclusion, we use the model for orthotopic xenotransplantation glioblastoma cells and analyze blood plasma by terahertz and infrared spectroscopy. Possibility of terahertz infrared spectroscopy of blood plasma and machine learning methods in the diagnosis of glioma was demonstrated. Machine learning pipeline was proposed to extract the informative features with good results. Sensitivity, specificity, accuracy over 19%. And at the next stage, the proposed machine learning pipeline will be tested for diagnosing glioma in human blood plasma. And our acknowledgement is thank you for your attention.
Thank you very much. Questions, please? You are welcome.
Thank you for your talk. In your infrared spectroscopy measurement, assuming you did your samples in air, then the infrared will show a lot of hydrocarbon as well as water contamination. Does this affect your result, or how do you get rid of it or take care of this? Thank you.
When we work with infrared spectroscopy, we put 5 microliters of blood plasma on special crystal and dry these samples. And we work with dry samples without, and we consider that water cannot influence on the spectrum.
Okay, thank you. Any more questions? Okay, thank you very much again. And we are going to the next speaker. It is Professor Cheng Chia Liang from National Donghua University, Taiwan. And his talk studied the life activity of regenerative worm Ailosoma viride using Raman spectroscopy and 2-photon fluorescence lifetime imaging microscopy. You are welcome.
Thank you, Mr. Chairman, for the introduction. My name is Jialiang Chen from Taiwan, and it was a long trip here and a lot of transition. If you know me, I'm not a person doing this, but my work is mainly focused on nanodiamond for drug delivery and the imaging and so on. I've been doing that for a while. But I think this is a side project from my group, only use spectroscopy method, and so we studied the activity of regeneration of a very small freshwater worm called Ailosoma viride. Okay. If you cut them in half, they would grow back to 2 worms in 5 days. So that's amazing. I think that's something we all need. This work is mainly done by PhD student Pooja, and along with 2 undergraduate students, Wu Jiahua and Huang Peiyang, with contribution of Renate. She has a talk tomorrow, please come. And also Dr. Atasha Kamanian and Elena Previdenstiva from the Lebedev Institute. And Atasha is in my group. And also collaborate with, this problem actually has come from the biologists. So Chen Junhong, a good friend of mine, they have been studying this from the biology point of view. The question, okay, when the life form is active, okay, what does it mean molecularly? So say a small organism is very lively, active, and then in terms of molecular structure or molecular substance, what does it mean? What is the molecular signal for the so-called life activities? So we think non-invasive spectroscopy method like Raman spectroscopy and confocal fluorescence and also FLIM, they are ideal to study this issue. Maybe we can find out what's going on in this system. Oops, sorry. Okay, we have studied many systems before, and we found they have one thing in common. If this bioorganism is active, and we always can observe a very strong peak, we call it carotenoids. They are very strong. We have seen this in zebra larva system. We have seen this in the elysoma. We have seen this in plants. We have seen this in amoeba. So they are all the same. When they are active, you see a strong signature from the contribution of carotenoid. And this is the elysoma virus I will be talking about. They are very small, less than 1 millimeter, but they are ideal candidate. They are ideal specimen for study the function called regeneration. So, talking about regeneration, and there are many species. If you cut them in half, they grow back. They lose a limb, they come back. So, but these are animal or organism. They are too big. Their regeneration process too long. Probably not ideal for laboratory study. So we studied this elysoma viret. As I said, it has a head, a trunk, and the tail, 3 parts basically. So if you amputate it, means you cut it into 2 parts. And the amazing thing is the head will grow a tail back. The tail will grow a hair back. That's amazing. Okay, so we like to understand what's going on. So just give you a brief idea about the regeneration process of this amazing elysoma. This cartoon shows this is the full worm, the head, a trunk, a tail. If you cut it, amputate, right? And I'm actually more interested in the so-called the part that grows back a new head. Okay, this is anterior generation. So this part without the head, in 6 hours, the wound will be healed if you cut it. Okay, and then in 24 hours, it will start a process called blastema formation, and then this is the secret we try to understand. The plasma formation means the original cells in the organ or in the tissue has already specialized in their function, right? So they will undergo a so-called de-differentiation. That means they will inversely go back to kind of like a stem cell. And then this blastema proliferate at about 53 hours after you cut it. And then this blastema will patterning, means they will decide which parts will go back to the original organ of the head. And then finally, in 112 hours, 5 days, you have a new worm. So what's going on in terms of molecular spectroscopy in this? So the question with regeneration study is, what is the molecular mechanism underlying on this so-called regeneration? Either it is a small species or bigger, high-level people, something like that. And the complexity understanding the cell signaling mechanism has not been answered. The response to repair after injury is less understood. Like I said, a huge data set, but no explanation from the biology sector. So the unsolved question in the regeneration study is that at the molecular level, a crucial question is how plasma get established in the amputee. So that's the secret, okay? So the plan of the study would be we use Raman spectroscopy, study the molecular signature. I mentioned about carotenoid. It is in resonance with the green laser. So in another word, we are doing so-called resonance Raman spectroscopy using the green laser, which is the most easy laser we can use. We like to know what is the role of the molecular signature signified in wound healing and plasma formation. So how the molecular signature is trying to tell us anything. In vivo detection of reactive oxygen species, superoxide SOD1s, and then they are participate in the process of regenerate, and we use 2-photon lifetime imaging to get beautiful imaging as well as study what's the mechanism in this regeneration involved. Molecular signature of this erythema, if we take a full intact worm and A, B, C, D, 4 different positions, you will see they have different distribution of a carotenoid. And so if you amputate, cut it, at 0 hours, freshly after you cut, you see this is the head, this is the tail, this is the original one. So you cut here, your head is here, your tail is there, and then focus on the wounded places. You will see B and C, only in A, which is the intact worm, you see the carotenoid signature. On the B and C, the cutting area. Right after you cut it, you don't see the signatures. So that's the beginning. And by the way, this is the keratin molecule we talk about, but we mainly focus on the CC double bond, which is a new one band, this band, and just to indicate how strong, how weak they are. So then the immunity of, the innate immunity of the erythema is, if you do a time-dependent Raman spectroscopy from 0 hour all the way to 8 hour, and then you collect the carotenoid, you list it. So at the edge of 6 hours, like 5.5, 6 hours, you see a surge of the carotenoid. So I mentioned at 6 hours, the wound will be healed. So just this indicates the carotenoid was sent to the front line to help either defend or repair the wounded area. So that's why you have a higher accumulation of the carotenoid. So this is evidence from the Raman spectra as well as the confocal imaging. So at 0 hour past amputation, we see a lot of reactive oxygen species develop in the wounded area, which is normal because these cells are destruct damage, so a lot of ROS can be observed. So we label the ROS. If you merge together, it's at the tip of the wounded area. But after 6 hours, the wound healed. So you have only residual ROS left. So that's what we can tell from the confocal. From Raman, the same. This indicates the quantity of the carotenoid is directly related to the number of ROS generated. So they must go there and do something to eliminate this ROS. And if you take the FLIM, fluorescence lifetime imaging, these are beautiful images. A and B are from intact worm. So you see the blue dots are lipid-rich area. And if you focus on the tip, the yellow part with the fluorescence lifetime, we think they are from they are from the ROS. So this is echo what we saw on the confocal fluorescence plus the Raman spectroscopy. Now, let's look more carefully. I think perhaps I show you another page first. Oops. Okay, never mind. Oops. No, sorry, can you go back to the... No, go back. More. Where I left, go ahead. One more. Okay, let's start from here. Sorry, mess up with the arrow. This is a 0 hour. We observe the ROS, and this is from the film. We can see the ROS at the edge, at the cutting place of the worm. So now if we look at the SOD, which is it's expressed at the amputee's edge of the posterior region at different hours. So we observe this overexpressed SOD1, which is the gene, in this area at the 5.5 and 6 hours. So that means after 5.5 and 6 hours, there's a surge of this SOD produced coming to the wounded area. But we also said at this time period, carotenoid also generate, right? So we did two different experiments. One is to express the SOD1, the other one is to collect the carotenoid, and they are the same. That means the only reason carotenoid would go to the wounded area in large number is to do the job just like the SOD. That's what we found. So you can see the expressed SOD1 and gene in the wounded area at this hour and 6 hour. So at 6 hour, the wound will be healed. That means you would have less ROS remaining there. Let's go to next. So you will see at this either superoxide or the SOD1, they are expressed with limited residual in the so-called wounded heal, because at this time the wound has been healed already. Okay. Now let's look at another process, the fluctuation carotenoid during the blastema formation. I said you form a blastema formation, and then this blastema is going to develop further into different organs of the worm. So at that time, if you observe the carotenoid, you see the fluctuation of the carotenoid from 9 hours to 24 hours. That means this fluctuation is accompanied with the process called blastema. Okay, this is what we can say from this data we have. After one day, at 24 hours, the blastema has formed. They start to develop and proliferate. So that means they start to grow into different functionalized organs and so on. So you will have quite limited area or pocket that you have this ROS, and if you monitor the SOD1 expression, it's also confined inside the worm, not on the edge of the so-called wounded area. And then this circular, oval circular shape is the blastema formation. From there, they will start to develop. Okay. So this is 24 hours, and if you observe from the film, it is the same. This is the blastema that the ROS is localized inside and gets smaller and smaller as the blastema proliferate here. So after 2 days, the blastema start to proliferate, to grow back a new head, right? So the ROS will be along with the direction of the growth. That's why you see the ROS, which is elongate in the shape that's indicating this part is grow, but still you have some reactive oxygen species plus superoxide remaining. And then after one day, you see a huge surge at roughly 72 hours after the amputation. So, but you will not see the ROSs. It means they are growing, they have become healthy, new worm again. So you don't see in any of these places we took the imaging, confocal image, we don't see any ROS. So we talk about a dual role of carotenoid. On one hand, it's an antioxidant, and they come to rescue, they kill or they scavenge the ROS and the superoxide. On the other hand, they provide antioxidant possibility for the cell. So if we look at this area, 7 to 96 up to 120 means they form a new worm. The SOD1 expressed only at earlier age, but up from this point onward, there's very little ROS remaining. And so what is the keratin? What is the carotenoid trying to signature in the anterior amputation at the initial stage? There is link between the carotenoid and plasma formation that I have just mentioned. It is a potential antioxidant and potent scavenger for the reactive oxygen species to prevent maybe the death of the worm itself. So that's the function we have seen from the Raman signature as well as confocal and the phlegm. So you amputate, and from the amputee side, the plasma will be formed. Reactive oxygen species generate, superoxide and ion generate, and carotenoid scavenge for antioxidant. So this is the process we think which is the function of the carotenoid in the regeneration process of this worm. And similar study for zebrafish, but zebrafish has much longer growing back. You can't cut zebrafish in half. You can probably amputate one limb or a fin. So that's not complete for a whole process of regeneration, but we get support from the zebrafish study. So the conclusion is Raman spectroscopy serves a very good so-called non-invasive method or tool to study some life activity. What exactly in the molecular level in the regeneration of edisoma. We can clearly understand the participation and dual role of the carotenoid in cell signaling and proliferation, differentiation in the regeneration using this spectroscopy method. But I have to confess, there's still one secret we didn't crack down. It's why the plasma will de-differentiate into sort of like a stem cell and then further grow back through the proliferation process. But this is only the beginning of this project. So this, I think it's a quite interesting project, so I report it to you today. Thank you very much for your attention. I thank also National Science Council for the support of the money. Thank you very much.
Thank you for an interesting talk. Questions, please? We already have questions. You're welcome.
Thank you very much, Charlie. Very interesting results. You focused your study in the role of vibrations in carotenoid molecules. So why carotenoid? do you think that other molecules can be involved in the process? I remember that in the first studies long ago, in the first experiments trying to see difference between live cells and dead cells by Raman spectroscopy, it was stated, but that coherence of oscillations, level of coherence is specific to live cells. When a cell dies, coherence is lost. Do you think that your results can be somehow related to that?
Well, I have to be a bit more humble on this one because I'm trying to reveal God's secret, I think, this project if we go along. Why carotenoid? Because we accidentally found in many different systems, when they are actively growing, you will see the active growing of the carotenoid. So we suspect this molecule may play some role in the activity and regeneration and so on. I also have to confess this is only our beginning on this project. I think what you have just mentioned, I think that probably will be happening because life is, I always thought physics is difficult when I was younger. Now I think, no, physics is a bit easier now and biology is difficult. I don't think I answered your question, but because I don't know.
Okay, thank you.
Thank you.
Thank you for presentation, and my question is quite general. You spoke about worms, regeneration in worms. Is your result have any correlation with human tissues?
Oh, don't promote me too much. Of course, people study regeneration with the aim to apply in human medicine, right? So we'll get there. We will get there.
Thank you very much for your great, interesting presentation. I have approximately 100 questions, but I ask only one for now.
Let's do the first one.
Carotenoids are lipophilic, so it means that it's very poor soluble in water. How do you think, in this particular worm, how carotenoids are transferred from some place to the wound? Okay. Is it the diffusion or some selective target transfer?
It's a very good question. Actually, I forgot that part. Usually, animals don't produce carotenoid de novo. I mean, they have to take in the carotenoid from outside. For this particular worm, they feed on small bacteria in the water that, like algae, they have carotenoid. So before we do experiment, we want to make sure we're not looking at the food rather than the worm. So we usually starve the worm for at least 1 day and change into clear water. Then we start to do that. So to answer your question, they have to depend on their food, and then they store the carotenoid inside. That's for all the animals the same. That's why we need to take carotenoid from the food. Carrot has a lot of, that's why mom and dad asked us to take a lot of carrot, right?
Okay, thank you.
And I have a very short question. So what was the procedure of cutting the worm? So it was like mechanically using a really sharp knife, or it was like lasers, or something like this?
Laser, you burn the skin, and then you have more chemistry involved, so you don't, mechanically.
Okay, thank you very much.
It takes practice, Yeah. They are so small.
Yeah, because it's very small.
Okay, thank you again.
Thank you very much.
And we are going to the next speaker. It is an online talk by Dr. Ivan Bratchenko from Samara National Research University, and his talk is Raman-based liquid biopsy of chronic heart failure patients. You're welcome.
I hope you may see me and you may hear me. So
yeah, we see you and we are hearing you.
Today I will talk about the liquid biopsy of heart failure patients. So please tell me if everything is okay. I may start.
Yes, can you start? Запустите, пожалуйста, полноэкранный режим, и мы готовы слушать ваше выступление. Вы можете начинать выступление. Запустите, пожалуйста, полноэкранный режим. Мы вас слышим.
So this study was conducted in two Samara universities, in National Research University and the Medical State University. Here you see the collaborators. So first of all, a short plan of my presentation. I will talk about the motivations for research. Then I will show you the cost-effective Raman microscopy system for liquid biopsy, and I will give you some examples of Raman spectral preprocessing, and in the end, some data regarding the accuracy of liquid biopsy for different diseases and possible applications in biomarkers. First of all, why it is important to create novel diagnostic tools for different diseases. I demonstrate this illustration very long time. It started from the start of my investigations of optical biopsy of skin cancer. This slide, first of all, demonstrates that heart diseases and cancer occupies the first two places in the structure of mortality, and that is really important that the medical errors occupy the third place. In this regard, it is very important to create a very precise, very sensitive systems for detection of diseases, of course, including heart diseases. And if we are talking about optical methods of diagnosis, we have two strong opportunities. First one is the optical biopsy, and the second one is liquid biopsy. During the optical biopsy, one may apply optical methods for the analysis of tissues in vivo, and this slide demonstrates this part of the study. Actually, if you are interested in this part of the study, you may contact me or look at the previous publications. And today I will talk mostly about the liquid biopsy. What is the liquid biopsy? You took a part of blood and try to analyze it with optical techniques such as Raman spectroscopy. But if we are trying to create the really suitable method for clinics, this method should be not only stable but also as cost-effective as we can imagine. In this regard, we try to create a liquid biopsy technique based on the cost-effective Raman detector. We utilized 785 nanometer laser for the analysis, and that is really important. The cooling, there is no cooling of the spectrometer detector in this system. That means that the system operates at the ambient temperature. The second step that makes this approach cost-effective is the application of silver nanoparticles. This is a really super costly way to create the stable slide, and in this application we only utilize the aluminium foil. We dry a zone of silver nanoparticles on this foil and then simply depose the drop of the sample of the blood on this substrate and dry it at the ambient temperature. What we will have in the condition of cost-effective Raman system. First of all, let's take a look at the conventional Raman signal. This is example of serum analysis. In this example, you see that there are only a few Raman bands that we may detect with cost-effective Raman system. And of course, such spectra is not suitable for analysis. If we will add the magnification of the spectra due to the CERS effect, you see this is a blue line, how the spectra changes, and we see an enhancement factor up to the million. And you see the newly appeared bands, and what is really important also in this approach, that there is no addition of silver nanoparticles to the spectra. The gray line represents that there is no any useful signal from the substrate. So, of course, first what we should analyze is if such approach is stable. And if we will try to measure multiple spots on this problem slide, we will see that the standard deviation is less than 8%. However, for different slides that we may utilize in our analysis, the standard deviation increases up to 17%. But still, if we compare the CERS spectra and the conventional Raman spectra, we may see distinctly the newly appeared bands that may help us to analyze the chemical composition of the studied samples. So we performed the collection of the blood samples in the hematology department of Samara Medical University and in different Samara hospitals. In total, we analyzed almost 300 patients and 80 healthy subjects. In total, we have more than 2,000 spectra for plasma and more than 1,000 spectra for serum of different diseases. If we'll take a look at the Raman data sets, one may see that it is really, really complicated to find any bands that may be useful for analysis. And even after the pre-processing of such data set, you see it on the right bottom slide, you see that it is actually hard to predict what bands will be really useful for the prediction of the diseases. So the easiest way to analyze data set is to analyze the mean values of these data sets. This slide represents how they may compare the data sets for kidney diseases and for healthy volunteers. We may next calculate the difference for these data sets and detect the most useful bands that may be utilized in the diagnosis. Of course, this is the easiest way to perform analysis, because if we'll take a look at the sample spectra, green line represents the healthy volunteer example, while the red line represents a patient with kidney failure. You see that there are specific bands that strongly differs for healthy subject and a person with some disease. In this regard, it is really, really easy to create a classification model that will get almost 100% accuracy, and the area under curve for such methodology is 0.98. So everything ends that we are trying to compare the groups of two diseases. For example, to differentiate the heart failure from kidney failure, and in this regard we'll have to utilize different chemometric techniques, and one of the most widely used and really suitable in this case techniques is PLS, the projection on latent structures. These techniques help to find automatically the most informative bands in our spectral data set, and separate these data sets on the basis of different diagnostical tasks. The most important in my experience point here is the application of cross-validation for the analysis of the constructed models. Because it is really easy to overestimate the model, because if you create the model, the blue line represents model error. One may apply a lot of principal components to create a really accurate model, but if you perform a cross-validation, you will see that the huge number of principal components leads to the instability of the model. And in this regard, only a few first principal components may be effectively utilized in the analysis of such Raman datasets. So what we get as a result of PLS analysis? This is an example of so-called VIP distribution, the variable importance in projection. And you see that in yellow on this slide, there's highlighted the most informative bands in the spectrum of patients with heart failure. You see that an algorithm may automatically detect the most informative bands that will appear the most effective in the separation of this exact disease. So, as a result, what we may achieve? The sensitivity, specificity are above 80%, and the total accuracy is more than 85%, while every other curve is more than 0.9. Of course, this is quite a good result, but at the same time, according to the medical guidelines, the most suitable, the perfect methods for application in medicine should reach 0.95 area under curve to be translated into clinics. In this regard, it is suitable to apply such powerful tool as a neural network. And we try to create a convolutional neural network that consists of 3 different layers types that are presented in this slide to improve the result of different diseases classification. So for the analysis of heart failure patients, we may see that CNN application strongly outperforms the classification based on PLS. And what is really important, this accuracy, the area under curve is more than 0.95. In this regard, this methodology based on cost-effective Raman device and application of neural networks helps to improve the analysis of diseases based on liquid biopsy that will be suitable for clinical applications. Of course, there is a huge question regarding to the application, especially regarding to the application of neural networks, is problems of black box nature of such classificators. And of course, we have to somehow understand what type of analysis use our created classificator. One of these approaches also utilizes the weak distribution, as I demonstrated for PLS analysis. In this approach, once again, we may highlight the most informative bands. Moreover, we may applicate this approach for the analysis of exact components in the tested blood specimens. For example, this slide represents the analysis of creatinine in the urea and the analyzed plasma samples, and one may see that both PLS and CNN demonstrate quite high values of correlation coefficients, but at the same time you may see that these values are not so high as values for chemical methods of analysis. And that's because this is only our start of this project, and we are trying to improve the analysis of exact components in the analyzed blood samples. And in these steps, we will have to measure the pure substances on the series slides and incorporate the predefined information about exact Raman bands that contribute to these exact chemicals to the classification models. And I hope this will help us to improve the analysis of exact components. So, in the end, I would like to say that this is a really super simple and thus cost-effective Raman system, but still it is maybe suitable for screening applications. And what is really important, despite the applications for kidney failure or heart failure that I mentioned, such liquid biopsy systems may be utilized in cancer analysis or diabetes or other diseases and in other liquids analysis. But of course, we will have to perform much more studies to prove this concept. And I would like to say thanks, first of all, for my wife, Ludmila, who created a huge part of this work, and our medical collaborators, Professor Lebedev and Professor Squatter from Medical University, my PhD student, Sahar, who run all the experiments, and Professor Tupikova from Chemistry Department. And of course, thanks for funding, and thank you for your attention. I will be glad to hear some questions.
Thank you very much. And you are welcome for questions. Thank you very much. Now we can ask questions.
Thank you very much for your interesting talk. I have some concern about the specificity of the results which you showed for in case of heart failure. Well, actually, in most cases, the patients suffering heart failure, they have concomitant diseases like diabetes, hypertension, and so on. How come that the results are so specific to heart failure? They should be most probably masked by the signals from other diseases.
Yes, this is a really good question. And in this regard, for example, one of the diseases that may mask heart failure is the progression of atherosclerosis, for example. So in our analysis, we collected the data from the patients with other diseases of head and vascular system. In this regard, this data demonstrated quite nice specificity. Of course, in the future studies, we will have to add other diseases for the analysis. But still, on the third stage, these results are quite promising. Because there is that's not a differences between the patients of between patients with heart failure and the healthy volunteers. It's differences between the patients with heart failure and patients with kidney failure, atherosclerosis, and in future steps other diseases. Yeah.
Thank you.
Thank you very much. And we are going next.
Thank you.
Yeah, thank you. Next, it is also an online talk by Professor Andrei Belikov from ITMO University, and his talk is laser drug delivery by radiation of visible and infrared lasers, efficiency and spectral study. Andrei, do you hear us?
Can you hear me?
Yeah, we hear you and see your presentation.
Great. First of all, I would like to say some words organizer who invited me to present my talk. Thank you very much. My name is Andrei Belikov. I am from St. Petersburg, Russia. I am professor of ITMO University and senior researcher of First Medical University. The title of my talk represent here. Drug delivery can be divided into systematic and local. Local delivery is preferable due to the absence of side and toxic effects observed with systemic therapy. However, local therapy do not penetrate the stratum cornea well. In my talk, I will focus on laser methods for improving the efficiency of local drug delivery. For improve the delivery of drug through the skin and other tissue, the mechanical, physical and chemical method can be used. Laser delivery is highly target, painless and low invasive. Local delivery can be applied in the treatment of wide range of disease. Of course, it can be used in dermatology for the treatment of patients with diseases of the skin and subcutaneous fatty tissue, which is more than 50% of the total number of patients in the world. Laser methods of drug delivery are very promising for local therapy of mucoses. Mucoses are fungal infection of the skin and nails. Up to 40% of population suffer from mucoses. In my talk, I will mainly focus on the treatment of onychomycosis, which is main fungal disease of the nail. In this case, laser radiation can be used for microaspiration, firstly, and for drug delivery through the laser format micropore. Drug delivery after microaspiration can be passive or active. Active delivery occurs under the influence of external factor, in our case under the action of laser radiation. In dermatology recently, photodynamic drugs have been used to treat mucoses. In this case, laser radiation can be used not only for biotissue microaspiration and drug delivery through the micropore, but also for photodynamic drug activation. At the last stage, under the action of light, singlet oxygen is formed and destroys the fungus. For the treatment of mucoses, methylene blue and chlorine-containing photodynamic drugs with absorption peak placed in the red region of the spectrum are most often used. Here represents the absorption spectra of water and the nail. It can be seen that in the visible range, the absorption of the nail is higher than the absorption of water. In this range, the absorption of the nail is determined by keratin and melanin as well as pathogens of onychomycosis. In the IR range, water determines absorption in the nail. Well known that the effective microaspiration, the laser wavelengths must be fit in the absorption band of the tissue. It can be seen that erbium lasers can be used for effective microaspiration of the nail because its radiation is effectively absorbed by water. Laser with wavelengths of 450 nanometers also can be used for effective microaspiration of the nail because its radiation is effectively absorbed by the structures of the nail. In my report, I will present the results of skin and nail microaspiration by these lasers. During delivery, it's very important not to change the properties of drug. For this, the wavelengths of laser radiation should not coincide with drug absorption peak. During photodynamic action, vice versa, laser radiation should effectively change the drug. For this, wavelengths of laser radiation should coincide with the drug absorption peak. Here represents the absorption spectra of methylene blue and chlorine-containing drugs, which typically used for photodynamic therapy of onychomycosis. It should be noted that the drugs mentioned here do not absorb in the IR region, so erbium laser with wavelengths of 1,540 nanometers and 2,810 nanometers can be used for delivery, but cannot be used for photoactivation. Radiation with wavelength 660 nanometer falls into the absorption peak of drug, and for this reason can be used for effective photoactivation. In our lab, microaspiration of skin and nail plate by visible and IR laser radiation was experimentally investigated. This slide shows the experimental setup which we used for our investigation. Here shows photographs of microaspirated nail plate in vitro by radiation of erbium lasers and lasers with wavelengths 450 nanometers. You can see that microaspiration of the nail plate was possible. The diameter of micropore in the range from 200 to 400 micrometers. Here represents the dependencies of nail plate microaspiration efficiency and ablation rate of the energy density and number of erbium ELF laser pulses. You can see that for this case, the maximum nail microaspirated efficiency was 9.9 micrometers per millijoule, and ablation rate was 3 was 38 micrometers per pulse. Here represents the dependencies of the nail blade microapparition efficiency and ablation rate on the energy density and number of erbium glass laser with wavelengths 1440 nanometers. You can see that for this case, the maximal nail microapparition efficiency was only 0.07 micrometers per millijoule, and the ablation rate was 5.5 micrometers per pulse, which is more than on other low than for the erbium ELF laser with wavelengths to 1810 nanometers. Here represents the results of microapparition investigation for lasers with wave-tight lasers with wavelengths of 150 nanometers. You can see that for this case, the maximum nail microapparition efficiency was 1.47 micrometers per millijoule. Thus, for most effective microapparition of the nail is possible when used erbium ELF laser radiation. This slide shows a photograph of microapparated chicken skin in vitro by radiation of laser with wavelengths to 1810 nanometers and for 150 nanometers. You can see that microapparition of the skin was possible. The diameter of micropore is in the range from 200 to 400 micrometers. This slide shows the microapparition efficiency of skin with erbium ELF laser radiation. You can see that for this case, the maximal skin microapparition efficiency was 15.4 micrometers per millijoule, and ablation rate was 57.5 micrometers per pulse. This is more than for a nail because the water content in the skin is higher than in the nail. Here represents the microapparition efficiency of skin with laser radiation at wavelengths of 450 nanometers. You can see that for this case, the maximum skin microapparition efficiency was 15.7 micrometers, what is close to microapparition efficiency for erbium ELF laser with wavelengths to 1810 nanometers. Thus, the effective microapparition of the skin is possible by the radiation of both investigated lasers. In this part of my talk, I will focus on laser active delivery of photodynamic drugs to the laser microapparated nail and skin. Here represents the scheme of the setup for investigation of active drug delivery under the nail and blade. We investigate active delivery of methylene blue and chlorine-containing drug Chlorder and Revixan. We compare the rate of delivery of an aqueous solution of methylene blue and chlorine-containing drugs under the nail by radiation from different lasers. We observed that delivery was not possible for all combinations. You can see here. You can see that for all drugs, the highest rate of delivery is observed for erbium ELF laser, but radiation with wavelengths of 450 nanometers demonstrate delivery rate close to erbium ELF radiation. We also compare the rate of delivery of an aqueous solution of methylene blue and chlorine-containing drug through the skin by radiation from different lasers. We observed that delivery was not possible for all combinations, as for nail. You can see that the rate of delivery of methylene blue radiation with wavelengths of 2810 nanometers and 450 nanometers are comparable with each other, and an aqueous solution of chlorine is delivered faster by radiation with a wavelength of 450 nanometers. In this part of my talk, I will speak about the study of spectral conformation of methylene blue and chlorine-containing drug after erbium laser radiation and after red light photodynamic exposure. For investigation, the effect of active drug delivery on properties of drug, we studied the extinction spectra of the drug before and after the laser irradiation and after PDT treatment. On the left graph of the slide, methylene blue expansion spectra are shown as function of the number of microsecond pulses of the erbium ELF lasers with an energy 4 millijoules. In the original spectrum, two peaks at wavelengths of 610 nanometers and 665 nanometers corresponding to absorption by methylene blue dimers and monomers are represented. It can be seen that as the number of laser pulses increases, the methylene blue extinction coefficient increases too. This may be due to an increase in concentration of drug due to the evaporation of water in the aqueous solution. Also, we can calculate specific exposure and coefficient of spectral transformation. Coefficient of spectral transformation in this case equal to ratio of extinction coefficients of the methylene blue at wavelengths of 665 nanometers and 610 nanometers. The dependence of the specific exposure and the coefficients of spectral transformation on the number of the laser pulses is shown in the right part of in the right graph. It has been established that when laser exposed with a specific exposure sufficient for active delivery, the spectral transformation coefficient decreases. This indicates that under the action of erbium ELF laser radiation, the conformation state of methylene blue changes and the number of monomers decreases, which can be reduced the photodynamic activity of methylene blue. However, the coefficient of spectral transformation after laser exposure remains greater than 1, which indicates that in the initial solution, in the aqueous solution of methylene blue after laser exposure, monomers of methylene blue are present to a greater extent rather than in the dimers. Thus, on the other hand, laser delivery by wavelengths 2810 nanometers increase the extinction coefficient of methylene blue, increasing the photodynamic efficiency. And on the other hand, it reduces the spectral transformation coefficient of the methylene blue, reducing of photodynamic efficiency. PDT action with wavelengths of 656 plus minus 10 nanometers after delivery reduced methylene blue absorption due to its photodestruction with formation of singlet oxygen. But you can see that after delivery and PDT treatment, the absorption of methylene blue more than in initial solution and the coefficient of spectral transformation more than in initial solution. So, after laser delivery with ELF erbium lasers and PDT treatment with red light, the PDT effectiveness of methylene blue can be increased. The slide shows the extinction spectra of chlorine-containing drug Revixan as a function of the number of sub-microsecond pulses. The erbium ELF laser with an energy of 400 millijoules. In the original spectrum, two peaks at wavelengths of 655 and 710 nanometers corresponding to absorption of chlorine E6 monomers and tetramers are represented. it can be seen that with an increase in the number of pulses, the extinction coefficient and the coefficient of spectral transformation equal to ratio of the drug extinction coefficient at wavelengths of 655 nanometers and 710 nanometers increase. Thus, the laser exposure at wavelengths of 2810 nanometers, the number of monomers increases, which can increase the photodynamic activity of Rivixan, like two we observed with methylene blue previously. PDT action with wavelengths of 656 plus minus 10 nanometers after delivery reduce Rivixan absorption due to its photodestruction with the formation of reactive oxygen species. But you can see that after delivery and PDT treatment, the absorption of Rivixan more than initial solution, but the coefficient of spectral transformation less than initial solution. It can be seen that the absorption coefficient increased in 1.3 times relatively to initial solution, while the spectral transformation coefficient decreased only in 1.50 times. So, after laser delivery with erbium laser radiation and PDT treatment with red light, the PDT effectiveness of Rivixan can be increased. In the final part of my talk, I would like to share the
Excuse me, but you have 2 minutes.
Of in vivo treatment of onychomycosis. We performed an in vivo study of laser microapparition, active laser delivery, and PDT of the chlorine containing photodynamic drivers, Rivixan for treatment of onychomycosis. The protocol of studies represent on the slide. The slide also shows photographs of volunteer territory before and after treatment. We measure the ratio of the area of healthy nail to its total area. It can be seen that after 3 sessions, this ratio become equal to 100%. What is patient fully recovered. Here represents the conclusion. Thank you for attention.
Thank you very much. We have time for one question. You're welcome.
Andrei, very interesting talk. May I ask a question about the optimal depth of the laser perforation of the nail plate? Do you have something on this recommendation or?
If you speak about this, we think that necessarily perforate the nail plate
totally.
and stop before the nail. The epidermis which locate under the nail plate.
So you have to perforate totally. Thank you.
Yes.
Thank you very much. And we have one more speaker. It is Professor Elena Genina from Saratov State University, and the title of her talk is The Study of Laser-Assisted Skin Optical Clearing in Vivo. You're welcome.
Thank you. First of all, I would say many thanks to organizers for kind invitation. And my talk will be about development of plasmon laser photothermal therapy with laser-assisted skin optical clearing. Please, next. Please, next. It is well known that the fight against cancer is one of the most serious challenge facing modern medicine. Therefore, with the development of conventional method of tumor therapy as surgery, chemotherapy, radiation therapy, photodynamic therapy, new approaches as, for example, plasmon photothermal therapy are developed. Plasmon photothermal therapy, or PPT, relies on the accumulation of plasmon nanoparticles in tumor tissue and the local heating under laser irradiation. Many different kind of nanoparticles as nanospheres, nanostars, nanocubes, nanocontainers, etc. Are used for PPT. Several works demonstrated their gold nanorods are the very effective agents for PPT due to their longer lifetime in the bloodstream, colloidal stability, easy turning of their plasmon resonance to the laser wavelength, and efficient conversion of light radiation into thermal energy. We studied the combination of gold nanorods with plasmon excitation wavelengths about 100 nanometers with laser irradiation because it penetrate deep enough into tissues and provide effective photothermal effect. We used nanorods with dimensions 41 nanometers per 10, about 10 nanometers, with plasmon excitation resonance in 808 nanometers. And laser irradiation with diode laser. This is the result of modeling heating of tumor layers and skin during PPT using gold nanorods and laser irradiation. The optical, geometrical, and irradiation parameters were the same as an experiment, and we try to simulate the heating in the different depths of tumor. You can see the result of the modeling, and their high temperature rise was observed in capsula of tumor and upper layer of tumors, but on the skin surface their temperature was high enough. It was enough for severe damage of skin. I should said that the tumor was the model red cholangiocarcinoma. It is the model tumor which transplanted subcutaneously, and the particle distribution was assumed homogeneous in the tumors as after intratumoral injection. And experimental temperature dependence, and this is simulation. So we faced two problems. High laser scattering in skin led to a decrease in the penetration depth of laser radiation and heating of the lower layers of the tumors. And the skin damage during tumor hyperthermia was significant. Therefore, the objective of our study was development of possible approaches to increase the efficiency, selectivity, and the safety of PPT by minimizing side effects using the optical clearing technique. Our gold nanorods with aspect ratio of about 4 and functionalized with teolytic polyethylene glycol to increase biocompatibility and to prevent aggregation in blood and tissue. The model of red cholangiocarcinoma line PC1 was produced in 9 healthy male rats by inoculation of tumor cell suspension into the interscapular region. After the tumor reached about 3 cube centimeters, the animals were divided into 3 groups of 3 rats. There were control group without PPT, group with conventional PPT, and PPT with optical preliminary optical clearing. Before an hour before the PPT, rats were intratumoral injected with gold nanorods suspension, and PPT with laser radiation during 50 minutes were performed in the second group. And in the third group, before the procedure, optical clearing agent application was made, and the tissue was exposed with low intensity laser radiation for 10 minutes. It was made for accelerate their optical clearing of skin. And then laser radiation with power about 2 watts during 50 minutes was made as in the second group. To monitor the light penetration into skin during laser irradiation, we used optical coherence tomography measurements. And before the PPT and immediately after PPT, we measured diffuse reflectance spectrum. And after PPT, the rats were decapitated and tumor was removed and cut on some samples. Capsular, upper and lower part of tumors, and also skin and subskin layers. The samples were measured using a spectrophotometer with integrating sphere to total transmittance and diffuse reflectance were measured, and absorption coefficient and reduced scattering coefficient were evaluated using inverse Adin doubling method. These are the results of our experiments. This is images of the surface of the tumors and temperature dependence, time dependence of temperature on measured with infrared visualized during PPT. This is the result of PPT in the second group, and this is the third group. You can see OCT, optical cleaning agent application, the result of low intensive laser irradiation, and PPT after irradiation. The temperature during low intensity irradiation was no higher than 41 Celsius degree, and during PPT it was about maximal temperature was about 60-70 Celsius degrees. There are OCT images before and after 10-minute immersion and low intensity laser irradiation. This is intact skin and skin after application and heating by laser irradiation. You can see that we tested some immersion agents to choice for choice of optimal from the point of view the speed of penetration inside skin, and you can see that addition of DMCO to the glycerol solution accelerated the penetration and enhanced the permeability of epidermis, and the depth of light penetration was high in this was deeper in this case. There are spectra of diffuse reflectance before the procedure, black curve, after the first stage of PPT with optical clearing, red curve. After the second stage of PPT with optical clearing with high temperature, and blue curve, and the green curve, this conventional PPT without optical clearing. And you can see that during PPT with optical clearing, the shape of spectra was not distorted significantly. But in this case, we can see that the hemoglobin disruption and water, this is water peaks. The water, the tissue was the tissue was dehydrated. Oh, I'm sorry. There are results of evaluation of absorption coefficient and reduced scattering coefficient ex vivo. Only one animal was in each groups of intact skin without any treatments from the first group. The one animal from the second group with PPT after preliminary optical clearing, and in the third group with conventional PPT. This is skin was the absorption spectrum of skin was disrupted, and the maximal changes was observed during conventional PPT. And you can see the this is the spot, dark spot. It corresponds to disruption of hemoglobin and high dehydration of tissue. And scattering coefficient, the same, was differ from in control group. Sublayer skin layers, subskin layer, and tumor top and tumor bottom. So after our experiments, we obtained optical properties of main layers of model cholangiocarcinoma in rats, capsular, top part and bottom part, and also bordering layers of skin and subcutaneous tissue in the spectral range from 350 to 1,200 nanometers before and after PPT. Combined use of immersion agent with low intensity laser radiation with power density about 1.5 watt per square centimeters for optical clearing of the skin before PPT was proposed. And the effect of immersion agent, mixture of 70% glycerol solution and DMCO on the optical parameters of the skin, subcutaneous tissue, and model tumor in rats in vivo after hyperthermia caused by PPT was presented as a pilot result. Thank you for your attention.
Thank you. Any questions, please? You're welcome.
In your presentation, you have used two kind of like low intensity and the high intensity. Okay, in the presentation you have used low intensity and high intensity. So for example, if we use high intensity without the PPT, can the high intensity cause any damage to the skin or the tissue we used? If it does, how do we compare with the PPT?
So he's asking, он спрашивает,
I said the maximal temperature during high intensive laser irradiation was about 60 and 70 Celsius degree. The coagulation of skin and tumor tissues and dehydration of tissues. This is severe damage of. This is effect of forward to damage tumor tissue due to hyperthermia. The gold nanorods generate the high inside tumor, but tissue above the tumor, skin and subskin layer are damaged too very much, and optical clearing preliminary prevent the severe damage of health tissue, and tumor will be damaged, and the health tissue was not damaged in high degree. Okay.
Okay, thank you. Any other questions?
Yes.
You're welcome. Okay.
Professor, I have two general questions. My first one is how do you determine the dosage level? I understand it is based on the temperature, but on your slide 11, for 2 watts of power density, you have irradiated for 15 minutes, and for 1 watt it is less than 15 minutes. So on what basis do you determine the dosage level?
These doses was experimentally obtained, and we used histological study after different doses of particle injection and irradiation, and after this time and laser power, the most cancer cells were damaged. And I don't say that the optimal temperature was reached after 3 intravenous injection of gold nanorods with concentration 400 micrograms per liter, and or after intratumoral injection. Summary: the results were obtained experimentally.
Thank you. And one more question.
Yes. Did you estimate? Did you estimate the size of nanorods and the effector size of nanorods which you used?
The size?
Yes, on the effect and the effectiveness of your therapy.
This aspect ratio and dimension of the nanorods was good result in penetration and retention inside tumors. It was obtained with experimentally too, and it well correlate with their laser irradiation wavelengths. But maybe there are other sizes and other wavelength may give the well result too. In different studies by other authors, they showed that the effect was with 164 nanometers, maybe.
Thank you.
Thank you again. So, I would like to thank all the speakers and organizers. Our session is over. Now we have a break for lunch. We're a little bit out of time, but the next session is starting at 2:30 p.m. Thank you.
Нет, смотрите, значит, первый у нас будет ставиться, как бы, сейчас подумал, он уже 3 дня идет сообщение, как мне кажется, что следующий будет здравствуйте.
Такси не забил, правильно? И все насчет. Такси не забил. Все, правильно, интересно. По чем времени? Точно? Я просто скажу, почему запись новых этих выступлений просто не нужно презентация. А мы нельзя. А у вас даже так мы не понимаем. Я говорю, доступно привлечь сотрудники. А у кого фамилия вообще? Давайте. Завтра приду, конечно, приду, чтобы вместе с вами. Я могу принести большую планету. Вот какие темы. Ну это видимо, и вот это человек, который не новый, я понял. Ну да, сам ну знаешь, сколько вы все завтра будете спасибо огромное. Вот, а я надеюсь, что не возьму какой-нибудь значительный. Можно не будет, правильно? Нет, ну, подумал, как, участнику личного материала. Конечно. Я запутался. Да, конечно. У вас через да. А вот а? Нет, пока нет кофе-брейка. Молодцом вообще, отлично. Да какой энергичный, я никак ковид не могу. По-твоему, глаза. Болел, уже не зараз. Извините за юмор, извините за черный юмор. Если какой-то прошу, я уже 2 раза вроде нажал. Ну ладно, нормально. Ну, постковидный синдром, да, к сожалению, не ответить. Да, молодцом. Сейчас мы тоже с коллегами, я, конечно, что можно хороший. Вы знаете, я скажу почему. Вот, не узнаете. Значит, нет, я здесь понимаю, знаете, у вас сейчас другая система. Знаете, когда я запомнился? А там загрузили?
А вот нас не
ладно,
первых китайцев нет. Я не буду. Ясно. Ну сейчас я тогда посоветуюсь. Ну тогда, если... Ну давайте и где хотите? Тут сидеть? Тогда вы будете их представлять, я только посижу. Но они наши, что я буду их представлять? Мне неудобно.
Ну да. Ну вот этого старшина, если...
Но этого я представлю.
Понятно.
Сейчас я спрошу.
И, конечно, к сожалению, стандартный ответ нет. Да? Почему? Потому что мы, конечно, стараемся себе держать. С одной стороны, скол может, они точно, может, такое было.
Мы просто просили их подтвердить вообще принципы получения письма, и они не ответили ни на смс-сообщение, ни на подтверждение.
Когда?
Так, Ширшину сейчас я знаю. Там Ширшин почетный, но там где-то был Якимов.
Странно. Я в последнее время с ними сам не общался, но до этого, когда обсуждались доклады, они так рвали.
Странно. А меня обычно выходит на связь всегда. Ну, вы знаете.
Ну, давай, чуть-чуть подождем.
Подождем.
Это уже было уже такое, что мы включались ровно минута с минутой. Он имеет право во времени, конечно. Вот, это первое. Ну, да, с другой стороны, это... Нет, конечно, но с другой стороны,
как так? Ты подал загадку. Ну, сказали, что не будешь. Я написал уже, что вот так на 4 совет вечером на 160 баллов. Вот. Вы там книжку печатаете?
Ну, нет.
То есть мы через несколько дней прочитаем нормально?
Мы не будем печатать программу.
То есть это интернет?
Да, можно будет меняться.
Да я жду. А вы где здесь живете?
В университетской, рядом с МГУ.
Сейчас вы тоже?
Да, я знаю. Но мы его там не видели.
А это Тучин?
Тучин не знаю.
Он, наверное, академический. Ну, нормально там допустим?
Прекрасно.
А как вы
Мы
добираетесь?
нашли автобус.
Он найдет от главного здания.
Ну, мы его ловим в городке.
Ну, прямо около главного здания.
Ну, нет, он ближе к нам. Он мимо проходит, поворачивает на какой-то там проспект. Мичуринский, что ли.
Все, я понял, на Мичуринский.
И мы его там, на него садимся, и он нас прямо вот сюда.
Да, становится.
Мы так немножко по ботаническому саду.
Ну вот непосредственно в мою лабораторию
Мимо на кафедры идешь, мимо биологического факультета и там.
Ну, только приятно прогуляться.
ну там, они начинают как руководители, мальчик пешеход постарше.
Ну тут вообще все
шеф, да, я Андрей.
У нас русская сессия.
Даже Чарли с своими студентами.
Ну мы ждем.
Ну, это по ним. Нет, не по ним. А отдельно. Ну, Алексей. Другие. Бывает, почему вот ну, у вас какая-то такие ну, у меня такой обзор, следующий у меня так, ну и следующий ну да, зелененькая, да, вот зелененький лейбл. Сейчас, вот
То есть не будет?
Я уже следующий, я сумел, что хотел.
Нет, наверное, не успею.
Так, вот, смотрите. Да, отмечен. И вот да, я не сказал. Так, здесь пока нету. Не видно его. Ну ладно, я прошу самого. Вот как раз бывает.
Dear colleagues, we are waiting for the first speaker, so we have some problems to connect with him. I think that we will wait maybe 10 minutes and then we will continue our session. I think it's not good because some people just know the time of the talk. Есть, нет?
Нет, я хотела бы попросить микрофон, чтобы вас в эфире было слышно на сайте. Когда вы будете микрофон, вы не попадаете в эфир.
Сейчас уже идет там, да? Ну, сейчас, наверное, не надо, потому что мы ждем.
А он вообще зарегистрировался?
Он вообще не ответил ничего.
That is why we are waiting. Unfortunately, we have no other information about the speaker. Ну, я думаю, вот в среду планируется? Ой, говорю, в среду, что говорю, в пятницу. В четверг как раз хороший. Александр Васильевич, вы подготовьтесь. Ну давайте вы представляете, тогда скажете, что наша сессия открывается. Сейчас, Александр Васильевич, сейчас вас объявят еще.
Микрофон. Подойдите, пожалуйста, микрофон.
Dear colleagues, let me start our afternoon session with the invited talk of Dr. Alexander Priezhev, laser-assisted method in hemorrhagic research. Please.
This is an invited
talk. Good afternoon, ladies and gentlemen. My talk is related to hemorrhagic. This is a branch of science and technology and of knowledge which is still underestimated by the medical community in terms of diagnostics and monitoring of diseases. While people who do research, they learn more and more every year about the significance of the parameters describing the flow of blood in the organism. You know that blood never stops in the organism. You can draw blood into a sample and then it will be in steady state and it starts to suffer this unusual state. Yeah? But in a living organism, blood always flows. And the way it flows, or the amount of alterations in the flow parameters, determine to a very high extent the state of the organism, human organism, animal organism. Sometimes we feel not very well, we don't know why, but it appears that it is because the blood flow has changed. I don't even mean the extreme states of hypoxia, when you don't have enough oxygen. Transportation of oxygen is the major function of blood. But there are many other reasons to impair the state of the living organism. So we have been involved into the study of hemorrhagic characteristics of blood, And this paper and the results were mostly obtained by my co-authors, Andrei Lugovtsov, who is here, Peter Yermolinsky, who is also here and will present the next talk, Alexei Semyonov, who is here, and he will talk about some other stuff another day, and also a few other people. Sergei Nikidin, he is a professor mostly involved in laser diffractometry. Yuri Gurfinkel is a specialist in monitoring and studying the microcirculation of blood in vivo measurements. And Ki-Sun Lee, my former PhD student who is now working in South Korea and who was deeply involved in this research and obtained lots of results. So the outline of my talk is, this is sort of a review, yes? So I will, after saying the motivation, I will discuss mostly the techniques of laser aggregometry, laser tweezers, laser diffractometry, optical capillaroscopy, and if I have enough time, I will give you some examples of clinical applications. Though we have now lots of these examples, we have studied several hundred patients suffering such diseases, diabetes, hypertension, because every week we make measurements with blood samples drawn from these patients in our medical center, University Medical Center. You know that blood consists of plasma in which many dozens of different molecules, and including polymer protein molecules are dissolved, and also cells. Red blood cells or erythrocytes, white blood cells, different types, and platelets. Because red blood cells are the majority, several dozen times more, the concentration of red blood cells is higher than other cells, so the parameters of blood flow are mostly determined by red blood cells. And when we talk about red blood cells, we should know, while not even all clinicians know about that red blood cells tend to interact with each other, with other cells, and with, what is very important, with endothelium. This is the monolayer of specific cells, endotheliocytes, which cover all the blood vessels from inside, and the interaction with these cells determines to a large extent how the blood flows. So one of the result of interaction of red blood cells that they aggregate. They tend, when they stick together, by the way, in whole blood, the concentration of red blood cells, or what we say hematocrit, is so high that average distance between the cell, you know that the distance changes in the flow, yeah? But the average distance is about the same size as red blood cell, which means 7-8 micrometers. So they are very close together. So the probability of touching, of sticking together is very high. And when they stick together, they tend to form so-called aggregates, which start from doublets, and then they grow together into linear aggregates, which are called rouleaux, and these rouleaux then aggregate together, and they form a three-dimensional structure. This aggregation depends both
on the properties of the membrane and on the content of the surrounding plasma. If you wash red blood cells, wash from plasma molecules, then they do not aggregate. Washed red blood cells, they may stick together and they don't aggregate. But as soon as there are protein molecules in plasma, these proteins act as pro-aggregants. They induce aggregation in different extent. There is the major pro-aggregant is fibrinogen. Then there are gamma globulin and some others. And and unfortunately, after transferring my file into this system, I can show you the movie. But this movie shows that in real time, if two red blood cells just touch in a certain place each other, in normal conditions, they just crawl one upon another and form a double. It takes several seconds in real time. If they are in plasma or in serum, but if you put them into just a solution of fibrinogen, which is pro-aggregant in plasma, they don't aggregate. That's very interesting. So there is some synergy of different substances in blood plasma. So there is a lot to study the aggregation, and the aggregation itself was invented by nature in order to control the blood flow. It appears that in big vessels, red blood cells as large, relatively large particles, they migrate towards the center, forming so-called nucleus, while leaving some space near the walls, which is free of cells. And this space serves as it reduces the friction. And this is why in large cells, in large vessels, blood flows with lower hydrodynamic resistance. But when gradually blood comes to smaller cells, then these aggregates are destroyed, because aggregation is a reversible process, and this is how it looks in a three-dimensional state. And see, here it is the flow of blood in microvessels, and you see that the red blood cells, if the aggregation is enhanced by some reason, due to some disease, or due to intervention of some chemistry or some medical medicines, so they can form clumps which will reduce the blood flow. So unfortunately, though aggregation as a phenomenon has been studied for several decades, so far we do not know absolutely what the mechanisms of aggregation are. So there are only a couple of major hypotheses which describe the mechanism, but unfortunately, I don't have time to speak in more detail about that. And here are some photographs of red blood cells moving in very narrow capillaries and in larger capillaries. Unfortunately, in human body, there are very few sites where it is possible to make such photos or movies. Usually this is
done in animals. In animals, there are more sites where it is possible to do that, and you may see that when red blood cells, which usually in normal conditions look like big concave discs, when they flow in capillaries, they change their shape into something like parachutes, and this ability to reversibly change shape, which is called deformability, is another intrinsic property of red blood cells. So one intrinsic property is aggregation, and another is deformability. And if they would be rigid, if they would not have this ability to aggregate, they would not be able to squeeze into very thin capillaries. And in many types of tissues, like heart muscle tissue in the brain, the diameters of the vessels, of the most narrow vessels, is lower than the diameter of red blood cells. So rigid red blood cells would not be able to squeeze into that. So deformability is very important. And because of these two properties of deformability and aggregation, blood acts as a non-Newtonian liquid. Non-Newtonian means that viscosity depends on the flow rate. Now here, unfortunately, there is some disturbance in the which it says shear rate in seconds and minus first. So at low shear rates, the viscosity is high, and in a larger shear rate, viscosity is low. Why? Because the aggregates have reversibly been destroyed, and red blood cells elongated because of high deformability. And this slide also shows that in normal person, in healthy person, the viscosity is lower, but here there is also some disturbance. In a patient suffering ischemic disease, the viscosity is quite high. So, hemorrhagic properties are very much impaired in case of many diseases like ischemia, like diabetes, like hypertension, heart failure, and many others. So I will talk first about the way how we can measure aggregation of red blood cells. Several parameters describing aggregation. Well, certainly there are non-optic techniques to measure that, and they were earlier proposed, but now with the advent of lasers and development of optical methods, optics shows much more higher efficiency in such measurements. And the technique I'm going to describe is the aggregometry based on diffuse scattering. The idea is very simple. If we shine with a laser light on non-aggregated red blood cells, they are large particles, larger than the wavelength. Oh, usually there is not very important wavelength dependence, but usually it's done with red light. 10 times larger than the wavelength. This is why large particles mostly scatter in forward direction. But if they aggregate and form still larger particles, still more light is scattered to forward direction, according to the theory of scattering. This means that if we measure the intensity of forward scattering in time, so in time 0,
we stop the flow, which destroys the aggregates. Particles start to aggregate, and the intensity of forward scattering light goes up. And then it sets you rays showing that all red blood cells have aggregated. So processing this curve, different parameters of the curve, we can measure several characteristics of scatter, of aggregation. And certainly it is possible to measure the backscattered light. The curve will go in an opposite direction. Backscattering will be reduced because of that. So we have several apparatuses to measure that. Usually we use a chip, a small chip with a very thin capillary, and we somehow generate pressure to make blood flow, and during the flow time, during several minutes actually, we obtain different curves from which we can measure. Well, there are different geometries how it is possible to do that. And we are able to measure the following parameters. Aggregation index, which means the percentage of aggregated particles. Again, due to different diseases, these parameters can change. Either more particles aggregate at a certain time, or less particles aggregate. Then characteristic aggregation times. If aggregation is enhanced, they aggregate quicker. And also these times are different. One characteristic time shows the time of aggregation of small size aggregates. And another time shows aggregation of large rouleaus. These parameters may be different. So aggregation rate, which is somehow related to aggregation times, and hydrodynamic strength of aggregates. This is very important parameter, because if the blood flows and it is aggregated, like I said, the process is reversible. Regular shear stresses, they destroy the aggregates. But if the aggregation strength is enhanced, is larger than normal, higher than normal, then the regular shear stresses will not destroy them. And these aggregates can clump the flow in smaller capillaries. So this is a very important parameter. Another way to study aggregation on a single cell level is laser tweezers. Well, most of you know what laser tweezers are. This is a setup, a technique. The basic thing is a very sharply focused laser beam, either one beam or two beams. And it appears that if a dielectric particle appears to come into the vicinity of this waste, there are some forces that trap the particle into the equilibrium position. And this technique was proposed by Ashkin, and probably you know that a few years ago he was awarded a Nobel Prize, not just for invention of laser tweezers, but he showed that how many biological, biomedical problems can be shown or studied with this technique. So the basic idea is that we use the wavelengths of the lasers which are not absorbed by the particles. This is why
though the intensity densities are very high in the waste, still the absorption is so low that the live cells are not heated, and we can perform measurements during sufficient time duration without any damage to the cells. So typical trap size is a couple of micrometers, and typical light intensities or light power in the trap is about several dozen milliwatts. And it appears that using this such device, we can trap red blood cells by the sides and measure the forces of aggregation and the forces of disaggregation, and this is the only way to measure such forces, because the forces are about piconewton magnitude, piconewton. You can't measure such low forces by any other technique. So this is what we've been doing in many So, and there is another way of making measurements. If you don't want to trap red blood cell by the side, you can stick different microbeads, for instance silica beads, to the membrane, and they are stuck very, very tightly, and the efficiency of trapping of a spherical particles with higher refractive index is higher. This is why it is more efficient to trap by these microbeads, and then you can manipulate with the laser beams, and also measure, for instance, deformability of red blood cell. Deformability, how high forces are needed to deform red blood cells. Unfortunately, this is not very adequate to the flow conditions. In the flow, the forces are applied not to certain points. The shear stress, the shear forces, they are applied to the whole membrane. This is why we usually use another technique, which is called laser diffractometry. So, supposing there is a monolayer of any particles, including red blood cells, and you shine with a laser beam, then you will, because they mostly diffract light in small angles, you will see a diffractive pattern. So the intensity reduces if you go farther from the center of this diffractive pattern. So if the position of the particles is stable, then the diffraction would be stable. If the particles are round-shaped, then the isointensity lines will be spherical or also round-shaped. However, if you put the deformable particles into a flow and you shine with a laser beam onto the flowing particles, then the particle would deform, elongate, and you will see on the observation plane an elongated pattern. Also, you can construct isointensity lines, and you can define the deformability index as a ratio of A minus B
above AI plus B. And then if you change shear rate or the velocity of the flow, you will see the dependence of this deformability index on shear stress. And this will characterize the ability of red blood cells to deform, which we use in our experiments. And again, could you please switch? Yeah. So originally this technique was proposed in 1970s. And still, since that time, several companies produce the devices, commercial devices, to measure deformability index and dependence on the shear stress. Unfortunately, in a sample of red blood cells, not all blood cells are similar. Their ability to deform is different, especially at certain diseases. At certain diseases, there are subpopulations of red blood cells who are stiff, while the others are deformable. And this technique does not distinguish that. It measures just average deformability. So in our laboratory, we have been developing an approach for several years already, and there are a few publications in that, because we know that if we have a mixture of red blood cells of different deformabilities, actually the isointensity line here, they're shown isointensity lines, they are not elliptic. They may be like rhombus or something like that. So we have developed several algorithms to measure different momentums of distribution of red blood cells in deformabilities, and we are also applying it to studying different diseases. So, and this slide shows how deformability index measured at 3 Pascal in shear rate 3 Pascal. So how the deformability index, which is about 0.3 at healthy person, how greatly it is reduced at different diseases like diabetic mellitus, chronic renal failure, diabetic retinopathy, and stage of renal disease. So you see the reduction. Nobody measures that in the clinic up to now. That's a problem. I said that clinicians do not take into account all these things. And these things are very important, not to diagnose, say, diabetes mellitus, because to diagnose diabetes you should measure sugar, but to monitor the state of the diseased person. And this is very important, because the impairment eventually, because the loss of deformability, blood flow is very much impaired. And because of that, this state of a patient suffering from diabetes is much worse if there were not the person did not have those impairments. Okay. And I should stress that all these measurements are unfortunately made in vitro. So you have to draw blood from an organism. And like I said, blood in vitro suffers, some people say suffers from these not natural conditions. And we have to always to show that it is actually what we measure in vitro, it resembles what is really in vivo. And this is not always easy. And one way to do it is another way that we are developing, is to image the vessel, microvessels, in vivo. Well, you know that since long ago, the technique of laser Doppler flowmetry has been developed, and many countries now produce different commercial devices. In our country, there is only one company which produces such a device, which measures the intensity of blood flow in the skin, and also with special endoscopes it is possible to make these measurements in the stomach, on esophagus, and some other places. But this is average intensity of blood flow, or perfusion rate. It is very important to measure that, but it doesn't show much in sense of hemorrhology. It is more important to measure in small capillaries, and there are very few sites on the human body where we can do that, and one of these sites is the eponychium. This is a very thin strip of skin around the nail. While ladies used to cut it away to make nails more beautiful. But in terms of medical applications, it is important to have this strip. It is called nail bed, and nail bed capillaries. So we have developed a special microscope to image these capillaries. Actually, we don't need very high magnification, but the problem is that there is also trembling. Even if we don't see trembling, even in normal healthy person, there is always trembling. So these images are very unstable. So we have to develop a grabbing technique, programming special brain to make it stable. And unfortunately, I can't show you the dynamics. It doesn't work here. But if you image normal capillaries in a healthy person, you will see rather high flow velocity, around 1 millimeter per second, very high. But if you image a capillary from a diabetic person, this is hypertensive person, you see the amount of aggregation and the flow velocity will be reduced. But in diabetic person, the aggregates are larger, the flow velocity is lower, and the shape of the capillary is also turned. So we are now estimating the aggregation properties, also processing such images. So this is an in vivo approach. So I have discussed a few approaches to estimating the aggregation properties, the formability of red blood cells, and they determine the hemorrhology, the blood flow characteristic, the blood flow quality, and eventually the state of our organism. I should say that when we processed the results of our measurements, we could even predict that the development of microreologic characteristics develop in such a way that we can predict that the person unfortunately will not survive during a certain time. So there is a predictive property of this research. Well, I don't know. Probably I don't have more time. I could show you several results like that. For instance, this is half time or characteristic time of aggregation for in a control group. This is around 10 seconds, while in a group of patients suffering type 2 diabetes mellitus, it is about twice as low. Time is lower means quicker aggregation, which is not good. Yeah? This parameter shows you the hydrodynamic strength of aggregate. In control, in diabetes, you see hydrodynamic strength, and this is statistically significant difference. Aggregation index in diabetes is also, and so on. So we have very many examples like that shows that in disease, these parameters are very, very different from normal case of healthy individuals, and this is why, to our understanding, this is very important to introduce this into clinical practice. So one of our aims to educate medical people, so this is why we try to often discuss with them these results. Usually medical people, clinicians, they are very busy. They are busy with patients. They are not very open to some new things like that. But this is one of our aims, so we are doing that. Okay, I will. Well, and there is one interesting thing. We back, please. So we construct such microrheological profiles of patients. So we plot so many axes, yeah, and we plot certain level of normal values, and we measure different parameters. Some parameters can be higher than normal, some lower than normal, and if we make such a profile for a certain individual, so this individual can be characterized hemorrhagiologically about his or her hemorrhagic state. We think that this is quite... next slide, please. So we think that this is very important. So I tried to persuade you that laser optical methods make it possible to create effective tools both for studying the fundamental mechanism of interaction of blood cells as the basis for blood microbiology and for monitoring pathological changes in hemorrhagical parameters. Thank you very much for your attention. Next slide. Yes.
Thank you very much.
There's one question.
Please, questions?
So thank you very much for very impressive lecture. I have a question about optical tweezer. Two questions. First one, what is about power of your laser? Is it low enough to not destroy your red blood cell?
Yeah. As I said, the output power can be rather high because there are many optical elements that reduce. But what is important is the power at the waist. So usually it is from several to several dozen milliwatt. If you calculate the power density, it may be megawatt per square centimeter. But because the wavelength is in the minimum absorption spectrum, we and many other authors estimated possible heating effect, and it is a few Kelvin during, it depends upon the time, yeah? some during, say, 10 or 15 minutes of measurement, we don't usually need more time. So we are sure that in our conditions, we don't destroy it. While there are there was some research performed showing that when you use tweezers to trap and manipulate different other life cells, like sperms, like bacteria, you should make preliminary research about application to these kind of cells, to these absorption properties.
Okay, and second question for general understanding. How you calibrate your dynamometer on the level of piconewton?
Sure.
How you calibrate it?
Say that, but before measuring quantitative measurements, we have to make calibration, and there are several ways to calibrate it. We use usually hydrodynamic approach. So we trap a cell, and then we make a flow, and we calculate which friction forces drag a particle from the trap, and we compare it with the trapping.
Okay, very interesting. Thank you. Sorry.
Any question? Oh, please.
So thank you, Alexander, for the very nice talk. And my question is about the deformability of erythrocytes. So you mentioned that current clinical protocols lack the measurement of deformability, and so this could improve the diagnostics. And my question is, what are the characteristic times of variation of deformability parameter? So is it like days, weeks in a patient with diabetes? And what are typical variations within small periods, like 1 day? So what is the standard deviation of deformability value within 1 day in a patient with diabetes, for example?
You mean a result sorry. Yeah. When we perform in vitro measurements, certainly the results will depend how long you store blood outside the organism. Yeah? So a special group, international group, studied this question, and they published a paper of recommendation that all such measurements should be performed during 2 or 3 hours after drawing blood. So we say freshly drawn blood. If you mean that.
No, I mean, say I will take the blood in the morning and in the evening and make 2 measurements from the same patient. Will the difference be significant or not? And in general scale, what are the typical times when there are some changes in deformability index value? So how do they correlate with the progression of the disease?
I understand that. In an organism, many different factors affect red blood cells, including your food. This is why a recommendation for all measurements is that you draw blood before breakfast. And you don't do measurements with blood drawn in the evening. But if you mean the effect of disease, I would say that this may be days if the changes of characteristic parameters of the disease change. For instance, there is a rise in sugar content. So it is known that sugar content also oscillates during day, yeah. But still, as the disease develops, the average amount of sugar, for instance, and some other parameters. So due to disease, the difference may be several days. But in practice, in our practice, we compare after several weeks. It is impossible to make a person to take blood every day.
So there is no sense to make it daily.
Yeah.
It's about several weeks. Okay, thank you very much.
No questions?
Thank you again.
Thanks, Professor Prieja, for nice presentation. And we are moving to another talk. Unfortunately, for any reasons, we have several cancellations at this session, so we just need to listen only one talk. And this one talk will be given by Piotr Yermolinsky from Lomonosov Moscow State University, and his talk entitled Correlation of Red Blood Cells and Platelet Segregation Measured in Vitro by Optical Techniques in Blood of Patients Suffering from Arterial Hypertension. This is an invited talk. Please, Piotr.
Thank you for introduction, and I hope you hear me well. And good afternoon, ladies and gentlemen. And today I'm going to tell you about correlation of red blood cell and platelet segregation measured in vitro by optical techniques in blood of patients suffering from arterial hypertension. And the structure of my talk will be as follows. Firstly, I'm going to talk about red blood cell and platelet segregation. Then I'm going to tell you the main aim of this study. Then I'm going to briefly talk about methods we've used. And then we're going to talk about results and conclusion. So let's start. And firstly, there are two processes: platelet segregation and red blood cell segregation. And these processes are quite different, because platelet segregation, it occurs only if you're injured or some vessels are ruptured or break out, and there are different. So there are firstly platelets. It's activated, and then activated platelets can combine together, they can attach to the endothelium cells, and many other things occurs. But other, that's not all, sorry. I'm not doing anything at all. Okay, thank you very much. So, something is going on.
Demonstration.
It started with the word breakout, that I said. So, and the next slide, please. And the next one. And another process is red blood cell segregation. This process occurs all the time simultaneously in our body, and moreover it is reversible. So these red blood cells aggregate producing in our bodies, and then they just separate it into single cells going through capillaries. And next slide, please. This is a really good video about sorry, we couldn't play it, but it just shows us about the property of red blood cells to reversibly aggregate. So if we diminish the flow, we observe that red blood cells start to aggregate, and then we can then break these aggregates into single cells, and so on. And next slide, please. And moreover, all these processes of red blood cell segregation and platelet segregation are quite differs for different pathologies, and especially arterial hypertension, diabetes mellitus. And in this study, we studied the correlations between platelet aggregation and red blood cell segregation in the blood of patients suffering from arterial hypertension. And of course, we studied it in vitro by optical techniques, especially about optical techniques that Alexander Vasilievich was talking about the previous talk. And the next slide, please. And we studied both platelets and red blood cell segregation by aggregometry method. And as Alexander Vasilievich said, aggregometry method is quite easy to understand, barely an inconvenience. So we have some beam, laser beam commonly, and we illuminate the chamber with the red blood cells or platelets, and this beam somehow scatters forwards or backwards. But the main idea that the scattering, forward or backward scattering, depends on the scattering object. So if it is a single red blood cell or just a large aggregate, it just scatters light differently. And we've used two different devices, RARE-scan for our red blood cell segregation measurement and Biola for our platelet segregation measurement. And next slide, please. And laser aggregometry is quite easy. So you have a chamber and two chambers connected with the microchannel, and we can control the pressure between these two chambers. So we can control the velocity of blood in this vessel, and moreover we can control the shear stress forces in this vessel, and we can control the aggregation state. And in this picture it is presented the measurement of hydrodynamic strength of aggregates. So it means this CSS, I will not talk about details, but we can measure the main idea that we measure the strength of aggregates. So the more the CSS, the harder, the more power, the more velocity of blood is needed to break red blood cells aggregate into single cells. And it's a very important parameter because maybe there are some aggregation and it's normal, but it's very hard to break these aggregates into single cells. And this is one parameter that we measured, and another parameter. And next slide, please. Next slide, please. It's a short video about measurement of CSS. So we have chamber, and we have some graphs. We have intensity of light. It's backscattering light. It just increases, then decreases, and we see that based on these kinetics, the aggregation state inside this microchannel. And next slide, please. And another parameters that we measured. It is measured on this cuvette. And we measured three different parameters, such as aggregation index, characteristic time of aggregates formation, and EMP parameter. And it is based on another idea that we just have a volume of aggregated red blood cells. So we just somehow break all aggregates into single cells, and then we start measuring the forward scattering light, and we measure the kinetics of aggregation. And here we measure aggregation index as some parameter characterizing the aggregation in a time limit of 10 seconds. So the more aggregation index, the more aggregation it is. And also characteristic time of aggregation formation, so just the less time, the shorter, the faster red blood cells start to aggregate. And next slide, please. And another approach we've used is laser aggregometry of platelets. And for this point, we've used Biola device. It is based also on the same principle. So we have some cuvette with the platelets-rich plasma. We somehow eliminate it with the laser beam, and we observe forward scattering light. And if we add some inducer, for these experiments we've used ADP inducer, it's adenosine diphosphate, for two different concentrations of 1 and 5 micromole. And adding this inducer, we can observe the whole kinetic of producing platelets aggregate. And in the Biola device, it is implemented two different methods, like aggregometry method, or it is also called, especially for platelets, turbodimetric method, and another method based on the analysis of light fluctuations, which is also used, so we can, it is a bit hard to explain in a minute, but based on fluctuations of light intensity, we can measure the average radius of scattered object. So the more fluctuations, actually, the less the radius. And the next slide, please. And here's the explaining of some parameters that we measured for different aggregometry methods, as we just add some inducer and we observe the increasing of forward scattering light, also increasing of aggregates. We measure the maximum aggregation degree and also the maximum aggregation rate. Also, we measured for method of light fluctuations, also the maximum level and the maximum velocity. And maybe we can come to the results and to the next slide about correlations. And on the x-axis, it is presented the red blood cells aggregation parameters. On the other axis, it is presented platelets parameters. And we see here for, maybe, I hope you see it well, that on the left graph, it is presented aggregation index versus aggregation degree. So aggregation index of platelets, of red blood cell aggregation, and aggregation degree of platelets aggregation. And we observe a weak correlation. So it means that it is, if for some patients red blood cells aggregation increases, it seems like the platelets aggregation also increases. Also, it seems for characteristic time formation, because the less time, the more the aggregation. And also we see aggregation degree, it is increased. And next slide, please. For some different parameters, we don't find anything. For example, we found some correlations only for high concentration of platelets aggregation inducer. For low concentration, like 1 micromole, we don't see any correlations at all. And next slide, please. So here's different aggregation rates. Also, it is somehow weakly, but still correlated with aggregation index and characteristic time of aggregates formation. And next slide, please. Oh, sorry. Yes. And it is very interesting that CSS, or hydrodynamic strength of aggregates, doesn't correlate with any other parameters. So it seems like the parameters of aggregation, just aggregation, they correlate with the platelets aggregation. But strength of aggregates somehow has different mechanisms, different properties, and it is also one proof that it is another parameter that we must consider into consideration. And next slide, please. And commonly said that there are some correlations of platelets and red blood cells parameters. And these correlations are not very strong. The index of Pearson, as you maybe saw, it was above 0.3, but still it's weak correlations. For some parameters we found it, for some don't found it. But very important and very interesting fact that correlations could be found only for high concentration of inducer of platelets aggregation. And my whole message is some parameters of red blood cells and platelets aggregation correlates weakly. And thank you for your attention. if you have any questions, I'll be glad to answer them, or you can ask me via my email, or just I'll be always here for these 2 days left for this conference. So thank you.
Thank you, Peter. And we have time for question session. If anybody have questions?
Okay.
Okay. Yes, Professor Tuchin.
Thank you for nice presentation. So, are you planning to make some measurements in vivo for real vessels, or what is the final goal of your work?
Yeah, so the final goal maybe is just, here I've presented only combined arterial hypertension patients. Maybe the final work will be a lot of groups of people, because in this combining there are people for the second or the third stage of arterial hypertension, and the final score will be that we have different groups of people, and we have maybe the stronger correlations for sure. And also we have some measurement of in vivo measurements with the capillaroscopy, as Alexander Vasilievich said. But we haven't done correlations with in vivo studies. So just now, from now on, it's just only in vitro. But further on,
and did you provoke some aggregation of the platelets by laser light, for example, or something else? Because if you provoke something, you can get more information about these interactions and correlation as well.
Provoke means?
Provoke, I mean, induce yes, by any external forces or something else, like laser beam, for example.
Yes, platelet aggregation was induced only by adenosine diphosphate, so ADP, only by this. So yes, there is no other inducers in this scheme. So, and in future also, it's planning to widen our area into in vitro measurement, in vivo measurements, because you know, in vivo measurements and in vitro measurements, it's not the same. And also we've published some articles 2 years ago about correlations of in vivo and in vitro measurements. And the same parameters, some of them correlated and some of them not, so it will be further consideration.
Yeah, thank you. Thank you.
I'm a co-author of this paper, but still I have a question.
Okay.
It is known that in that interaction with endothelial cells of both red blood cells and platelets changes a lot in rheology.
Yes, of course.
Do you expect that if you made such measurements in the vicinity of endothelial layer, the results would be somewhat different?
Surely there would be some different, because endothelium cells impact the RBC aggregation and also platelets aggregation sometimes dramatically, because they exhibit some kind of gasotransmitters and other stuff. So it will be a very, very big answer for this small question. So, but it will be different for sure. Okay.
Okay. And next question, Dr. Semyonov, please.
Thank you, Peter, for your presentation. Just a question. You say that you studied platelet aggregation and red blood cells aggregation.
Yep.
We know that when the blood vessel is damaged, platelets aggregate to cover the place of the damage.
Yes.
From the previous presentation of Professor Priyezhev, we know that red blood cells aggregation is the regulator of a little bit different thing. It is regulation of the flow, of the blood flow. So my question is, from the point of view of your results, how red blood cells, what role do red blood cells play in the aggregation of platelets during the damage of the vessel? What do you think? Do they help each other, or they're controversial? What do you think, basing on your results?
It seems like they help each other, because also in a coagulation process, red blood cells also play a crucial role. Of also they coagulate based due to the different inducer, and also it seems like they help each other to aggregate. They just has some synergetic effect, maybe it can be said like this. So it's just, if something is increased, it is expected that something will be increased higher.
Okay.
So
questions?
So thank you.
Okay, thank you.
Thank you very much.
Speaker again. Thank you very much. And unfortunately, due to the cancellations of other talks, we finalize our session for this. We have finalized evening session, and the next session will start at 20 minutes past 4. And you're all invited to the next session. Thank you very much. After the coffee break. And now you're invited for coffee break.
Вы случайно Сергея Виноградова не знаете?
Знаем. Мы с ним работали.
Он чем-то тоже похож на него.
Он вообще химик.
Метки
звал, метки, да.
Мы с ним собирались одну работу сделать, сейчас пока не получается.
Он, кстати, был в России после несколько, в 19 году перед конференцией была по биофотонике на корабле.
Да, вот там, по-моему, мы обсуждали как раз. Он просто заканчивал химический факультет. Я тоже с химического факультета.
Понятно. Ну, у нас сейчас в России есть химики тоже.
Я знаю, в Санкт-Петербурге там есть группа, которая температуру измеряет.
УНИК, да. В мире есть такой УНИК из университета. Да, и So hello everyone. So we start the next session with a talk by Yulia Alexandrovskaya from Institute of Photon Technology in Troitsk, and she will talk about optical coherence elastography, assisted monitoring and quantification of osmotically induced strain in biological tissues. So please.
Thank you very much. Okay. First of all, I would like to thank the organizing committee for the possibility to make this talk today. And my report will be devoted to osmotically induced strain in biological tissues and polymers, and its evaluation using optical coherence elastography. A few words about the principle we're working with. Osmotic effects can be found everywhere where there is a semi-permeable membrane and concentration gradient. So like it is shown here, we have two forces from the solution and from the solvent. One force is osmotic pressure, force on the membrane, and another force is solvent flow that intends to dissolve this concentrated solution. And the interplay between these forces may result in mechanical alterations of membrane or surface of polymers and tissues. And this is the effect we are going to talk about. Bright examples of osmotically regulated systems are biological cells, of course, like red blood cells. We saw it in the previous session. Also, porous polymers and gels, biphasic porous media such as, for example, soil, and of course biological tissues as a particular case of porous, water-saturated polymers and gels. Now, as I have told, diffusion is usually coupled with mechanical alterations. So some example is shown here when a concentrated solution, a solvent, comes into a body, it experiences swelling, mechanical properties change, and we observe even breakage of some chemical bonds and changes of dimensions of the system, and so on. There are several methods to directly observe this strain, these mechanical changes. We can divide them in two groups. The first group, so-called microscopic methods, like shown here. It can be electro-based, ultrasound-based, or magneto-based methods. They provide information on macroscopic scale. Usually the resolution is more than 1 millimeter. And the second family of these methods is nanoscale or molecular scale methods. A bright example is chemical-based methods, like atomic force microscopy, that allows to analyze nanomechanics of objects. However, till the very recent time, there was no method to close the gap between this macroscopic and nanoscale of analyzing the tissue mechanics. So we believe that optical methods are quite suitable to close this gap due to higher resolution than the macroscopic methods, and in particular optical resolution of optical coherence elastography can be tens of micrometers. And what is important here, so I won't stop much on this technique. I just would like to draw your attention that tomorrow there will be a plenary talk by Dr. Vladimir Zaitsev, and he will give more details about the approach that are about optical coherence elastography and the particular approach that we are working with. And here is just a brief detail of the principle of the working method of phase-sensitive OCT. So strains here are determined proportional to displacement gradients, which in turn are proportional to phase variation gradients of OCT signal. So that's the main general principle how the strain is obtained in this method. Again, for more details, if you are interested, don't miss the tomorrow plenary talk. And I will move to particular applications of this method for diagnostics. Here is our setup for osmotically induced strain observation. It's quite simple. So we have an object, we have a solution. So strain is induced by diffusion of a solution into analyzing object. And OCT is working in non-contact regime, so as it is shown here. So what we actually obtain is a structural image and a phase image of OCT signal as well. So by comparing two phase images, we get we calculate interframe strain, and then by accumulation of many interframe strains, we obtain so-called cumulative strain. That is a cumulative result of for some time of analysis, and further I will refer to this kind of result. So what we can actually get using this technique. This is an example of analyzing the dynamics of strain into polymeric gel, in particular polyacrylamide gel, and dependence of the strain on concentration of the applied hyperosmotic agent. Here it is glycerol, that is use different concentrations of glycerol. And what is interesting here, that we observe not only the dehydration, the shrinkage of an object, that is common knowledge for this kind of object. If we apply glycerol, so it leads to dehydration. But also we observe some unusual subsurface contraction effect. So shrinkage here is moving to blue coloration, and dilatation is moving to red coloration. So here it is yellow and orange and so on. So we have the general shrinkage effect accompanied by subsurface dilatation effect, which was quite unexpected. So next I will show how we can use this sign alternating strain for diagnostics. Here is just a comparative study of different optical clearing agents, for example polyethylene glycol and polypropylene. So we can just differentiate between the strength, the dehydration strengths of optical clearing agents, and the dependence of this strain and this distribution of sign alternating strain on the concentration of a solution, which is important for optimizing the concentration for optical clearing, in optical clearing techniques that affects the tissue integrity, the cells, and so on. So we can just analyze what kind of stress, what kind of tension will be applied to, for example, some cells integrated into this polymer or tissue. Next, I would like to talk about a particular application. It is the very recent result obtained for recent months, and it is about how this optical technique helps us to differentiate between different stages of cartilage degradation. So cartilage degradation for joint cartilage is known as osteoarthritis. It is a very commonly spread disease. And there are certain stages of cartilage degradation, and at the initial stage of degradation, the alteration, the structural alterations are so small that we cannot observe them by conventional diagnostics like CT or MRI or ultrasound. So we might say that nowadays there is no common effective approach for early diagnosis of osteoarthritis. At early stages, it can be just prevented and cured more effectively than in late stages where cartilaginous tissue is destruct or even absent. So in the early stages of cartilage degradation usually present the depletion of protoglycan content. Protoglycan is a component that serves for maintain a certain level of tissue humidity, so it absorbs water, and also stabilizes collagen network. So it is very important constituent of cartilaginous tissue. It was shown by many works that early stages of osteoarthritis are caused by depletion, somehow cleavage of this protoglycan content. So, as it is shown here by histological examination. In laboratory, we can create different models of osteoarthritis by applying a particular protease, trypsin, that depletes this protoglycan. So here is just shown here, like an example. And the effect, the level of tissue destruction depends on trypsin concentration and time of reaction. So we modeled different stages of cartilage degradation and what we just observed using this method. So strain was excited by applying glycerol of concentration 30% and 10 minutes of observation of diffusion. I have to note that these processes are observed during maximum 10-15 minutes after application of a solution. So it is strongly non-uniform, non-equilibrium situation is modeled when we can catch these features. And here we can see that we can easily differentiate between different types of tissues, like healthy tissue where protoglycan are partially depleted, and tissue where protoglycans are completely depleted. So here we see the common for polymeric structures distribution of shrinkage with subsurface contraction. For partially depleted protoglycan, we see very strong shrinkage and the contraction is almost absent, so we don't see it in graphs. And for totally depleted protoglycans, we see very weak signal of cumulative strain, so it is about 10 times less than for the healthy tissue. It tells us that the properties of this structure are completely different from the healthy initial tissue. Whereas at visual inspection and at ultrasound inspection, these structures are the same. Thank you. So I go to my conclusion. The osmotically induced effects can be visualized in porous liquid saturation media by phase-resolved optical coherence elastography with shown limitations. And the resolution of this strain is about 50 micrometers, which closes the gap between macroscopic and nano level. And sign alternating strain field are obtained for hyperosmotic and non-equilibrium regime of diffusion. And we can obtain results for different cartilage degradation degree using this developed technique. I would like to thank my colleagues from Biophotonics Laboratory in Moscow, and also our closest collaborators from Institute of Applied Physics and Saratov State University, and also to show some related publications to the topic. Thank you very much for your attention.
Вопрос, пожалуйста. Алексей.
Thank you very much for your talk. I would like to ask the question about the cartilage. How do you think, is it possible to use your method of OCT data analysis for any joint injury, for any cartilage damage, or like for example those who are deep in the body, like in waist or something like that, or only for some tissue which are very which is easier to detect, like for example in nose or in knees or something like that? Thank you.
Thank you for the question. This very approach was developed for joints, so we intend to use it for joints. As you may know, joints are now easily to be analyzed. So you have to open the joint to perform arthroscopy. So this technique is for arthroscopic evaluation of osteoarthritis. I think this could be done some tricks to apply this technique to another types of cartilage, as you mentioned. Nose, it is more easily achievable. Yes, it is possible, but you have to optimize your optical system in each way. So here it is optimized mainly for joints, and also is very important for implants, because sometimes we need to check the quality of cartilaginous implants. So they are used in medicine, like they are extracted, then they are analyzed, and they are implanted to a patient. Well, this is also a very good situation for this method.
Thank you.
Please, Valery Viktorovich.
So thank you very much for nice presentation. So many interesting results. So my question is, as far as I understood, that this technology allows to quantify spatial distribution of the osmotic stress or mechanical stress. So, and my question is, what is the, and you said that shrinkage of the upper layers due to osmotic action and some swelling, delayed, what does it mean delayed? It's swelling?
The opposite, shrinkage of the whole volume and contraction, dilatation.
So like swelling?
Yes.
This is medical stuff, they use swelling. Shrinkage and swelling. And for total is shrinkage.
Yes.
If you measure. So, and what is the time scale? It is after action of your osmotic agent. It's 1 hour or 1 minute, 1 second.
Yes, as I have mentioned here, it is the very initial stage of diffusion. So the maximum time that we observed this was 15 minutes. So it's first.
So for 15 minutes. Yeah, I understand. 15 minutes. So another point. It is very important to understand the time scale when water molecules will start to move. So if you have some, you understand. So it's so-called distant action of osmotic press. Can you, so because swelling, so my understanding that if you apply your stress from one side, it was one side or two sides?
It was one side.
One side.
One side.
So you're not touch, so it was one
Absolutely.
side application?
The bottom is isolated.
And another, the bottom part is isolated from the agent.
Yes.
So, and so you can estimate, so I think it's what I'm talking about. So probably the, you induce the water particle, water molecules to move. and they concentrated there. It's too far to go there, but still to the upper and to live. And therefore, this is the maybe explanation.
Yes.
And this is very important from point of view that your osmotic stress immediately start all water molecules to move with different result. Am I right?
Well, it depends on the depth.
Yeah, I'm talking about the depth.
In the subsurface level, analyzing by this method, it happens quite immediately. So you drop and you see immediately the result. And this shrinkage into 1 millimeter level, so we observe the maximum of shrinkage in time about 10-15 minutes.
Yeah, but you need water molecules to travel.
Yeah.
This is diffusion time.
This is diffusion.
Yeah, so I understand. Thank you very much. Yeah, good.
More questions? So then we thank the speaker.
And let's move to our next talk, given by Vladislav Czeslavsky. It is called Imaging of Molecular Oxygen Using Time-Resolved Phosphorescence. Please, you're welcome.
Thank you very much. This work actually has been done in collaboration with Becker Hicker, the Institute of Experimental Oncology from Nizhny Novgorod, and the company Scantel. So, as you know, probably oxygen is a very abundant element on the Earth. So this diagram shows that almost 50% of content in nature on the Earth. Yeah. So the next element is silicon-26, and the rest is very small contribution. So this is a very abundant, very widespread element on the Earth. So which forms of oxygen are in fact important? So two forms are well known and are important in our life. One is oxygen which is in triplet state, and this is very specific molecule. Not many molecules exist in the ground state in the triplet state. And another molecules which are important from oxygen is oxygen existing in the singlet state, excited state. And the singlet state is actually normally realizes when, for example, photosensitizer, which exists in the triplet state, collides with the molecule of the oxygen in the ground state, and then you get a singlet state of oxygen, and the photosensitizer goes to the ground state. Very interesting fact here is that the luminescence lifetime of the oxygen in the singlet state is very long. It's about 72 minutes in the gas phase. But when you consider it in the solutions, then it goes significantly down to like several microseconds. So why in general to study oxygen? Well, oxygen plays a lot of important functions in, for example, in redox reactions in the living cells. Yeah, and all the effects of hypoxia which exist in biology, for example, are related to deficiency of oxygen. So, for example, in eye diseases, it's important. In brain research, there's ischemia, hypoxia. When you study, you need to know oxygen content. Of course, in cancer research, most of the tumors they're hypoxic, And it's always interesting to study simultaneously the oxygen content in the cells in the tissues, and on the other side, for example, not only oxygen content but also the metabolic state of the biological tissue or the cell. Of course, also if we talk about the oxygen in the singlet state, it's important. Here comes photodynamic therapy. So in terms of the availability of the of how much singlet oxygen is generated there, yeah. So what is the way to study to get the information about oxygen content in the tissues? There are many different ways. So I will talk here only about the optical measurements now. Yeah, so normally, if you have some probe, chemical probe, normally it's probes which contain metals, and if you have such kind of a probe which collide, or which exists. Which can exist, which has a triplet state. When this kind of probe collides with the oxygen, the phosphorescence which emits from the triplet state to the ground state is quenched. And in this way, not only intensity of the fluorescence goes down, but also the phosphorescence lifetime goes down. Yeah, and these changes can be. These changes in the lifetime, phosphorescence lifetime, can be measured. Yeah. So when you want to measure phosphorescence lifetime and also fluorescence lifetime together, so that actually it's a bit tricky, complicated, and there are different reasons for these complications. The first reason comes from the excitation side. So when we talk about phosphorescence, we talk about milliseconds or microseconds phosphorescence lifetimes, yes? And this kind lifetimes require very low repetition rate of the pulses on the order of kilohertz or maximum 1 megahertz, yeah? So second thing is that there's a dynamic range problem, yeah? Fluorescence is a very intense process with high quantum efficiency, and in this compared to the phosphorescence, in this way, if you start to co-register both processes, you will kill the detector, yeah, with a very intense fluorescence light. On the scanning side, it's for phosphorescence measurements. It's required that the beam stayed in each pixel for quite a long time, yeah. So much longer than phosphorescence lifetime itself. So very slow scanning is required in this case. And the consequences of this long staying is that long acquisition times and the lysing of the laser repetition frequency with pixel laser repetition frequency with pixel frequency results in more effects, yeah, on the images. This is what you see on the lower corner, these stripes. So how can we measure avoid these problems and make measurements of together fluorescence and phosphorescence? So there's a simple way to do this, which we offered, and the way is the following. What you do, this is a pulse train, yeah, from the laser. What you do, you modulate your pulse train in such a way that when the laser is on, you record the fluorescence, and when the laser is off, you record phosphorescence. And this modulation can be done on the pixel dwell time, yeah. In this way, you can get from the same pixel, you can get the photon distribution for fluorescence, and on the other side, from the same pixels, you can get photon distribution for the phosphorescence. So the modulation, in this case, is the approach, yeah, to do both fluorescence and phosphorescence measurements. On the next slide, what you see as an example of realization of this technique. So these are the cells. The cells which were incubated with phosphorescent sensor ruthenium, which is sensitive to the oxygen, and they were recording of the signal from NADH. This is the most well-known endogenous fluorophore, which takes part in the redox reactions in living cells. And on the right-hand side, you see phosphorescence lifetime image, accordingly the scale for the same cells. Then for here, what you see also, there was the cells were affected with antimycin, which actually this chemical blocks the respiration of the cells. In this way, the oxygen is not consumed by the cells. And what you see here, you see a drop immediately. If you look at the phosphorescence lifetime image, you see immediately the drop in the phosphorescence lifetime. Yeah, because you have a lot of oxygen in the cells. Next slide presents actually human embryonic kidney cells, also this is phosphorescence lifetime image, and there's for comparison, for example, this is a palladium sensor, and phosphorescence has quite long lifetimes, around 100 of microseconds. So at normal oxygen pressure, and you see by the color here represent the phosphorescence lifetime, you see that when there's a normal oxygen pressure, or 22% of concentration, the lifetime is around 75 microseconds. When you go to the reduced oxygen pressure to almost zero, here actually it was you got around 144 microseconds, so it's almost double to the fluorescence lifetime. In the next slide, present actually the measurements of the oxygen in vivo on the mice. So you see here two areas. One area is it's a tumor here. And another area is a muscle on the mice, yeah? There's two areas. And of course, as we know, tumors are hypoxic, has hypoxia status. Yeah, so this you can see immediately if you look on the phosphorescence decay curves here. So in the tumor, when you measure, you get around 2.6 microseconds. Phosphorescence lifetime, this is the representative curve here for the tumor, and in muscle it's around 2.4 microseconds. So it's you can differentiate just by the lifetimes where the tumor and where's the muscle, where's the normal tissue. Next, I would like to discuss it was before we discussed the oxygen, I would say, in the measurement of the molecular oxygen in the triplet state. Here I will talk about the methods for singlet oxygen measurements. And there are basically two approaches based so one is wide field measurements are possible, another one is confocal. And there are, of course, for both of methods, it's possible to measure directly singlet oxygen and indirectly. So indirectly means one introduces some sensor for singlet oxygen and then measure the fluorescence of this sensor. And of course, both of the methods have advantages and pitfalls. For example, if you use synthetic singlet oxygen sensors, then there's a problem, of course, that the interaction of the singlet oxygen with the sensor competes with the interaction of singlet oxygen with the cells and tissues, and this reduces the photodynamic effect. And of course, if you add extra sensor to the living tissue, it's not desired due to the toxicity issues. But if you think about the direct measurements, of course it's most reliable and accurate methods to measure the singlet oxygen, but as we will see, it's quite experimentally demanding. So, and the main difficulties of the singlet oxygen measurements come from the fact that the efficiency of the phosphorescence generation, phosphorescent emission is very low. It's 1/millionth of in the solution. Yeah. And another difficulty for making such kind of measurements is that it's actually that there are no good detectors which have a quite good high. I would say not a lot of good detectors that have high quantum efficiency to record such weak signals in the spectral range of around 1.3 micrometers. Yeah, and this is the range where singlet oxygen emits. There's one solution to this problem, and the solution is to use superconducting single photon detector. Yeah, and the principle of work for this detector is quite simple. So you have you have a light which incidents on the stripe of the detector. It's the width is something very, very small, around 5 nanometers. So this single photon absorption causes the avalanche of so it breaks down the Cooper pair, and then you get an avalanche effect in the superconducting detector, and then you get a kind of a local heating here in this wire, and this local heating results in the creation of the resistance and consequently results in the drop in the drop in the voltage. Yeah? And this change in the voltage is registered as a detection of the photon. So this is the principle of superconducting single photon detector. And the good thing, the beautiful thing here is that these kind of detectors, they have terribly high quantum efficiency, almost about 100%. Yeah, so it's about, if you to speak strictly, it's about 95-98%. Yeah, in this spectral range. And moreover, they have a very, very low dark count rates, less than 1 photon per second. Yeah, so these detectors are very suitable to register such kind of very weak signals. So then, what we did, we used this detector in our system and our scanner. So one port was used to excite the photosensitizer, which was chlorine E6, and another input was used actually not as a entrance for the laser, but as an exit for the signal to the single photon counting detectors, superconducting detector. So if you put appropriate mirrors, you can detect not only actually the singlet oxygen using SSPD, but also the autofluorescence from the cells using normal detectors which are properly working in the visible range. So for excitation we used around 200 microwatts power, and this results in something like in the intensity of around 140 kilowatts per square centimeter. So the results came here. So it's you see it was a scanner. It was in a scanning mode, but we did first test measurements in the solutions. So on the first picture, you see the phosphorescence decay curve of the singlet oxygen in the solution with the phosphorescence lifetime of around 9 microseconds. But when we add when we incubate the cells with the chlorine E6, we see effectively the drop in the phosphorescence lifetime of the singlet oxygen, because of course there are a lot of cell constituents. Yeah? There are a lot of organelles in cells, a lot of different stuff in cells, so the phosphorescence start to become quenched. That's why you get quite significantly reduced phosphorescence lifetimes. So the next steps would be here to get the actually not only the decay curve, but to get the images of the distribution of this singlet oxygen across the cells. And this was singlet oxygen method measurements for methylene blue, and we got around 13 microseconds. Of course, as you can see, the collection time for the signal is quite long. It's about 300 seconds, so it's about 5 minutes for each curve. So it's quite slow process. So here comes the conclusions. So we think this is that phosphorescence lifetime imaging technique is an established technique for mapping oxygen in a triplet state and singlet state, and simultaneous oxygen and metabolic status of cells and tissues can be determined. Second, fluorescence lifetime imaging, phosphorescence lifetime imaging can be used for interrogation of singlet oxygen in solutions and cells, using confocal scanner with superconducting detector. And the last thing is that both fluorescence from the cells and phosphorescence from singlet oxygen can be recorded, provided the optimization of the system is done. So with this I will end my presentation, and I will thank you.
Let's thank the speaker. And the session is now open for discussion. Please, questions.
Thank you very much, Vladislav, for your nice talk. So, if I understand correctly, the main thing to differentiate between fluorescence, fast fluorescence, and phosphorescence is actually the modification of the excitation system. And for that, the initial train pulse, you modulate that it will be the train of larger pulses, yes?
It will be, no, you mean in terms of the pulse width, it's the same, exactly.
Yeah, I know. But the thing is that the excitation is a little bit different, that the fast component is, is happening during the excitation.
Yes.
That's why the excitation is so long, so you detect only the long component that originates from the phosphorescence. So my question is, this modulation of excitation is possible for any kind of picosecond laser source, or you need some special conditions, some special things that have to be done with which are very specific to your excitation source?
No, in general, most of the picosecond lasers, they can be, at least diode lasers, picosecond diode lasers, they can be easily modulated by modulating the current on the diodes, which is quite simply to do. So it's very easy. Yeah?
So you don't need any kind of special generator or something?
No, not normally.
Pulse modulator, so it's general approaches?
No, it's a general approach. If you talk about the modulation, let's say, of the femtosecond pulse trace from femtosecond lasers, then of course you need to kind of external generator to control the acousto-optic modulator of the laser, and then you can of course select the specific. You can do the modulation of the pulse train in this case. Yeah.
Thank you.
So, any more questions from the audience? May I ask one short question? When we speak about non-direct methods of measurement, when you use special probes, what are the sizes of this probe? So I mean, is it easier for them to penetrate, for example, dense biological tissues?
It's chemical probes like singlet oxygen green, which emits in the green range when it's collides with the singlet oxygen. It's nanometers.
So about 10 nanometers or 1 nanometer?
It's less than 10 nanometers.
Less than 10 nanometers. Yeah. And are there any other molecules that can quench this phosphorescence besides of oxygen?
Sure, yes, it's actually, this is what I said. It can be proteins, for example, which can quench the singlet oxygen. It can be anything, actually. In fact, there are a lot of constituents in the cells which are influencing the singlet oxygen. So measurements. So.
Thank you. Thank you very much. Let's thank the speaker again. And the next talk will be also given by Dr. Sheslavsky. It is called Resolving Ultrafast Fluorescence, Decays with Hybrid Detectors.
So this actually talk was supposed to be given by Dr. Wolfgang Becker from Becker and Hickel, but due to impossibility to come, so I give this. He gave me presentation, so I give this talk for him. So now I would say we go from the from the slow measurements to the fast measurements on the other side of the time scale. Yeah, and this talk is, I would say, it's more instructive. I would probably should have put it first, this talk, and then the second one. So here the outline of the talk. So I will talk about what does fluorescence decay function tell us, some principles of the time-correlated single photon counting film, and present the results on the fast decay measurements, and also present the results of the using fast detectors to study melanoma. So a lot of endogenous biological molecules produce fluorescence lifetimes, give fluorescence lifetimes in the scale from several hundreds of picoseconds to, let's say, 5-6 nanoseconds, and on the other side, actually, if we look at the chemical fluorophores, they also stay in the same range. It's, for example, rhodamine 110. It has around 5 nanoseconds in fluorescence decay time in water. Yeah, and here on the left-hand side we have an ADH recording. So for free NADH, which is not bound to protein, it's measured. The measured decay is fast decay is 400 picosecond. If this NADH is bound to protein, then you can get lifetimes depending on the what is the protein it interacts. It can be from 2 to 5 nanoseconds. Yeah. So we see that there are quite long lifetimes, and the question comes: is it the intrinsic nature of the fluorophores to have such long lifetimes? For example, even for NADH, it's pretty long. Or we just don't see something, and we need some better detectors, more fast detectors, to get registered some shorter lifetimes. And this question we are going to address in this talk. So conventional detectors, photomultiply tubes, they are used to have temporal. They have temporal resolution of around 250 picoseconds. Yeah, all detectors, and of course this is comparable to the lifetimes which I showed before. This is to around 400 picoseconds for the fast decay component of an ADH. Yeah, recently there were developed so-called hybrid detectors. And these are detectors which are actually quite interesting and nice compared to the normal PMTs. So this is the diagram how it works. So conventional photomultiplier tubes, they have many diodes. So when the photoelectron emits from the photocathode from here, it hits for the conventional tube. It hits many diodes, and then it loses energy. You lose photoelectrons. You have very low efficiency, and you have, of course, because you have many bunching elements, you have a very poor temporal resolution for the conventional photomultiplier tubes. Here, what was realized here, you have a one-step process. So the photoelectrons which are emitted from photocathode, they go directly to avalanche diode and cause the current which is registered by single photon counting electronics. Of course, you have to pay the price for this, because this one step only possible with the high voltages of around 10 kilovolts. Yeah, with the normal PMT tubes, you don't need such high voltages. But what you get a very good temporal resolution, which is around 120 picosecond for the early versions of the detectors. But still, if you look at this 120 picoseconds, this may be not quite enough, because, for example, it's known that melanin, which was measured earlier in the papers, there are quite a lot of works. It has people measure something around 100 picosecond lifetimes for melanin. So what we need, probably we need something even faster in terms of the detection time resolution. And then the new detector, which was developed maybe 3 years ago, from Becker and Hickel, was this HPM106 model with a time resolution of around 20 picoseconds. Yeah, this is extremely short. And what it means, if you have this kind of time resolution, you can register the fluorescence decay curves down to around 10 picoseconds. Yeah, so with the convolution processes. And this is nice. So, but now I go a little bit aside and tell in general what is the fluorescence lifetime, why it's quite nice in general. So, and the good thing about fluorescence lifetime is that in fact it gives information not only about fluorophore itself, but also about the surrounding medium. Like it gives may give information about, as we saw, about the oxygen content, give information about pH, viscosity, temperature, and many other parameters. So, and this is quite nice. And here, what we see here is one of the examples. So, there's a sensor for chloride. Quinine sulfate, and depending on different chlorine concentration, you can get a different fluorescence lifetime. You can easily identify this. Yeah, if you just measure the intensity, you don't see the difference. Yeah, but if you measure lifetime, you immediately get the difference. Yeah. In biological systems, as we know, many of you do FLIM here, know already about FLIM. In biological systems, it's not you have simply one exponential decay. Normally, you have several exponentials. Yeah, describe the decay curve. So, and each you can identify each contribution of each exponent by the amplitudes. Yeah? So if you have, let's say, three exponential decay, so you can get how much you have one component, how much you have second component, and third component, and so on. So what do we need to record such kind of complicated decay curves? First, we need a very good electronics. Yeah, so to have which has a lot of time channels which allow to record the curve with a very good precision. So the next thing, we need very fast detectors. Yes, to record the fast processes. Yeah. And finally, not finally actually, we need actually the detectors which work on the single photon counting level, so they should be very, very sensitive, not only fast, but also should have high quantum efficiency. Yeah? And finally, of course, you need, when you do imaging, you need a very good depth resolution for this. You need scanning, and you need but if you have, you need a two-photon excitation. So, and this is realized actually in our technique, time-correlated single-photon counting, using scanning and multi-photon excitation. So the next results, which will be shown here, are based actually on multi-photon excitation and single-photon counting using TCSPC and fast, I would say not fast, ultra-fast detectors. So this is the principle how the system works. So you get photon detected in one point of time, next point, and so on, and then you get the photon distribution across the sample plane. So here you see this is actually pig skin recorded with two-photon excitation, and you get a very clean image from the defined focal plane. So from the previous image you can extract the decay curve actually, and with this kind of approach, time-correlated single-photon counting, you can get a very good, you can perform very good multi-exponential analysis. And finally, if you use the detector, proper detector, with the, for example, this ultra-fast detector with IRF less than 20 picoseconds, you can detect resolve fluorescence decay times down to 10 picoseconds. So, and then the question again, do such fast decay processes exist? And now the examples. So this is mushroom spores. Wolfgang likes very much mushroom hunting, so he said we have to record these curves and see how the spores look like, what is the lifetime. And we found actually quite amazingly that the mushroom spores, if you make a fluorescence lifetime image, you get a very fast component, dominating actually component of around 17 picoseconds. Yeah, this is amazing. Of course, the interpretation should be done for this somehow, but so far this is just a fact. Yeah. Next, we recorded pollen grains from the flower here, and here we even went down. We recorded the fluorescence lifetimes around 10 picoseconds with a contribution of main contribution of around 90% of this component. And next, it's even amazing, and this is the most, so far I would say it's a world record. It was the fluorescence lifetime image of a human hair. Yeah, and what we got around 6 picoseconds fluorescence lifetime with the contribution to, it's a multi-exponential, of course, analysis of around 96%. So the system which uses this ultra-fast detector allows to detect this kind of fluorescence lifetimes. Of course, the flowers and the flowers and the hairs is quite interesting. But if we look for more practical examples, one comes to mind is melanoma. Yeah, and here. What we see here actually melanoma and normal tissue. And if you look at this is a normal tissue here, it shows fluorescence lifetimes something like around 200 picoseconds, this one, yeah. But melanoma can be easily identified by very sharp fluorescence decay, which is around 13 picoseconds. And of course, if you make a measurement of this area with the normal detector, what you will see that you will get a lifetime something like 100 or maybe 80 picoseconds. Yeah. And the nice thing here is actually you can in this case you can easily So in fact, you will not be able to differentiate between two areas, between melanoma and normal tissue. But using this kind of detector, the possibility to differentiate different areas becomes feasible. And the next slide is shows. I don't know. Can you switch? Yeah, it's a benign dark pigmented skin lesion, and here this it's a dark pigment and nothing wrong with that, and you get conventional lifetimes, which most of the people get for normal skin is around 150 picoseconds. So, in summary, we have the following thing. We have that ultrafast fluorescence decays can be found in different biological samples. So we found a dominating ultrafast fluorescence decay component in melanoma, and the component is not found in benign pigmented skin lesions. And we believe that it comes from a special form of melanin, presumably aggregates, which actually promotes the quenching and gets faster decays. And detection of the fast component could give insight into the tumor development. And finally, the fast detectors may improve the accuracy of fluorescence decay analysis of fluorophores containing a significant part of fluorescence decay. So this brings me to the end of this talk. Thank you very much.
Thank you very much. The session is now open for discussion. Please, questions from the audience. Yes, please.
Thanks again. Well, so now you modify the detector.
Yes.
And yes, it's great, it's amazing, yeah. And the question is, do you have to modify everything else, like synchronizing board, operating board, and so on?
Yeah, it's actually, I didn't tell this, it's a bit trick. Of course, if you use this detector, this ultrafast detector with old type electronics, you will not get these results. To get the correct results, of course, you need to modify also the electronics, time correlated sync photon counting board. And what is modified? Modify these so-called discriminators on the board, yeah, which select the pulses. So they are made much. The new electronics, which is used for this, was used for these measurements. It contains a fast constant fraction discriminators.
Okay. Thank you.
More questions, please. Yes, Professor Tuchin.
Thank you very much for presentation. So I would like to maybe to have some details about the last idea about the melanin.
Melanin.
Yeah, and so you have some particular data to have a conclusion that this is some kind of different melanin is aggregated and so on. Some additional proof
yes,
of this concept.
we actually this kind. In fact, this kind of measurements has been done using pump probe experiments. Normally, such kind of short lifetimes, very short dynamics is possible to measure only with pump probe techniques. And there are some works on pump probe for probing melanin, yes, and they measure these lifetimes, and they provide the information about that such kind of lifetimes may be attributed to the aggregates in melanin. And then we compare the lifetimes which we obtained with the data obtained by other groups by pump probe, and then we just suggested that this is the same mechanism, yeah, nothing else here.
So this is particular for melanoma, not other pigments.
It's particularly for melanoma. Yes. And I would say this is if we go, we now thinking about going to clinical applications. This is a much more relevant approach than using pump probe, which is quite complicated technique. Yeah. So,
yeah, thank you.
Okay, more questions? If we have no questions, we have to move further. Thank you very much. Let's thank the speaker again. And our next report will be given by Dr. Alexey Semyonov. It is called Protein-Mediated Carotenoid Delivery into Liposomes Affects Local Microviscosity of the Membranes as Revealed by Fluorescence Anisotropy. Please, you're welcome.
Thank you very much for the presentation of mine, and thanks organizers to be able to participate here in the conference with my report. Carotenoids were already mentioned today. It's highly studied biological active pigments which are contained in different species and even are produced in industry, in microalga, in carotenoid-producing strains of Escherichia coli for different applications, very interesting applications, because carotenoids possess unique antioxidant properties which are very useful not only in cosmeticals of functional food, but also in the clinical applications for treatment of various diseases which are accompanied with intense oxidative stress. But the thing is that such substances like carotenoids have some difficulties and challenges. So most of it is related to its highly lipophilic nature. It means that they're very poor soluble in aqueous solutions, and if we talk about organism, most of it is water and aqueous solutions. So all of these great properties are really limited with its poor solubility in aqueous media, and we might possibly try to overcome this by using some special platform of delivery, like maybe nanoparticles or something like that. But in this case, the carotenoids would lose their positive properties, and their chemical and especially photochemical stability will be low. But on the other case, there are some species in nature that also utilizes carotenoids for photoprotection mechanisms. These species, Cyanobacterium, they use photosynthesis in their life, so they need mechanisms to be photoprotected during photosynthesis, and they use carotenoids. And the thing is that centers of photosynthesis and the centers of and the places where carotenoids are produced in these species, in these cyanobacteria, they are different. So cyanobacteria have somehow moved carotenoids, transfer carotenoids from the place where they synthesize to the place where they function. How do they do that? They use special water-soluble carotenoproteins. And the most abundant in the nature is orange carotenoid protein. It is, for last decades, is one of the most promising and studied protein for different biochemical and biophysical applications because of its unique properties. Most of these properties are connected with its with this optical activity. This orange carotenoid protein consists of two dimers, dimer C and dimer N, and it can bind different carotenoids in the location between these two dimers. For particular this carotenoprotein, it was demonstrated its efficiency in the binding carotenoids and delivered to different membrane. But unfortunately, the set of carotenoids that can be bounded by this protein is limited. But the thing is that we can modify this protein to expand the number of carotenoids. And that was done, and a new protein was developed. It is called AIRON.CTDH, It is the dimer homologue of C-terminal of the part of OCP, and it was debris from Anabaema cyanobacterium strain. And the thing is that this carotenoprotein can bind a wide class of carotenoids that is called catacarotenoids. In particular, echinidone, this is molecular structure, is provided here, which is very effective as an antioxidant. For this protein, it was demonstrated that it can reversibly bind carotenoids and deliver it to the membrane with high efficiency, but it is in theory. In the present work, we have to solve several aims in order to study the interaction between this carotenoprotein and the membrane object. We need to characterize the efficiency of the delivery. So we need to develop some kind of parameter of the membrane to say that the delivery of the carotenoid by this protein is efficient, and what do you need to do to increase the efficiency in that case. As a model membrane, we choose liposomes made of soy lecithin phospholipid S75. It's a big component system. This is the cryo-electron microscopy photo of liposomes. You see that this is mostly monolamellar membrane structures. Well, some of them are bilinear, but it's, you see that it's mostly, we can say that's mostly homogeneous, with its mean diameter around 100 nanometers. What can we do with membranes if we want to study their properties? We can put the fluorescent probe in the membrane and to study the fluorescence properties of this probe and therefore assess the changes with the liposomes and their membranes. As a fluorescent probe, we used this body-pi based probe, which is highly lipophilic. It means that it can be bounded by liposomes, and the thing is that being bounded by the liposome leads to the significant increase of its fluorescence. Another positive feature of this probe is that its emission spectra overlaps with catacarotenoid absorption spectra. It means that we can use first resonance energy transfer to track the interaction between the probe molecule and the carotenoid molecule in the membrane, which is very useful if we want to study the efficiency of the delivery. We use the time-created single photon counting setup by Becker-Hickel with the picosecond excitation. And we measured not only fluorescence decay curves with the picosecond temporal resolution, but we were also able to measure the anisotropy properties of the fluorescence because we can change the orientation of the polarizer in front of the detector with the excitation of the sample with the polarized excitation. If we assume that the object is irradiated by the vertical polarized excitation, there will be emission originated from the photoselected fluorophores, and this polarization of this emission will be the same. But due to rotational diffusion, some fluorophores would be not organized, will be not ordered, will be disorientated, but they also would emit. And if we detect their emission which is not vertical, for example, which is horizontal, we will get another fluorescence. And here it is described as a red. As a red curve. And if we confront each curve with each other using this formula, we will get the curve of a new process which is characterizing the transition of the fluorophores from photoselected from ordered photoselected stage to randomized non-polarized stage. And this transition also depends on the environment, and in particular the viscosity of the environment. And the time, the characteristic time of this new process is proportional to the microviscosity. So in our study we measured fluorescence decay and microviscosity. First one is fluorescence decay. Well, on this video has to be the molecular dynamic stimulation of the interaction between carotenoid and the fluorescent probe, but it doesn't work, so you have to believe me on my word. The thing is that according to molecular dynamics, there are possible situations when the probe, which is described as a blue molecule, can be localized really close to the carotenoid to implement Fred transition. And this is illustrated on these particular curves of fluorescence decay. As the concentration of the protein with carotenoid increasing, the fast component of this decay is changing, and it is decreasing. It means that the part of the fluorescence is quenching due to Fred effects, and we can see how it is decreasing from 4 nanoseconds to 1.5 nanoseconds. It means that the carotenoids is delivered by the carotenoprotein to the membrane. It interacts with the probe, the transition takes place, and we can see the Fred. We can estimate the efficiency of this process actually on the by measuring the mean average lifetime on the concentration. And we can see that as the concentration increases, the efficiency of Fred is also increases. That's why we can say that delivery is efficient. Actually, using this information, we can estimate the minimum number of molecules that is delivered into one liposome. Let's assume that the thickness of the membrane is approximately 10 nanometers, and actually it is close to truth. Well, it depends on the phospholipid composition, on different factors, but still it is like around 10 nanometers usually. We know that we can calculate the Foster radius. It is the constant which is depend on quantum yield of the fluorescent probe. It depends on the refraction index. It also depends on the overlapping between emission and absorption spectra. And the thing is interesting is that it also depends on the orientation, mutual orientation between the fluorescent probe and the carotenoid molecule. According to molecular dynamic calculations, this coefficient is 0.68. So we can calculate this, and using this first radius magnitude, we can calculate the mean distance between echinonone, between carotenoid, and the fluorescent probe in the membrane. If we assume that both molecules are spheres, small spheres with their own radius, actually like this is about 68, 70 angstroms, we can, using a very simple geometric equation, calculate that according to 1000 nanomoles, so 1 micromoles concentration of the protein with the carotenoid, the minimal amount of the molecules that are delivered into liposome is around 800 molecules on one liposome. It is the minimum. It is the minimal estimation. So in this case, we can expect that microviscosity would change because a huge amount of the molecules was inserted into the membrane. And according to our measurements of the microviscosity, we can say that as we add more protein with carotenoid to the solution of liposomes, the correlation time increases. which means that microviscosity is increases. The thing is that what was pretty surprised that it was dependent on the temperature. The effect was significant at the temperatures below 25 degrees Celsius, and was insignificant at higher temperatures. We suppose that it is connected with the two-component phospholipid composition of liposomes, because different compositions of phospholipid can form different domains at different temperatures. So for such, it was a surprise for us that for such experiments, when we track the delivery process of something to liposome, one component phospholipid membrane are more suitable. Because the effects are not so temperature dependent. So, in conclusion, I would like to say that FRET-based approach provides indicative information on the efficiency of carotenoid delivery, and using this in combination with time-resolved fluorescence anisotropy, we can assess the effects of the delivery of carotenoids on the physical properties of the membrane, and therefore we can develop the indicative informational parameter of the efficiency, which we can use not only for carotenoid delivery, but also for the delivery of drugs or anything that can be delivered into the membrane. So that was work done with a collaboration with from different organizations, and I also have to mention the funding from Russian Sound Foundation, and if I have time, I can answer some questions. Thank you.
Thank you very much. Do we have questions from the audience? Yes, please, Professor Tuchin.
So very interesting. So I have a very quick question about the so high precision of the refractive index, which you showed us on the last slide. So yeah, you see here 1.4251. So you took it from the literature, or what is the origin of this data?
Yes, it is the literature data that according to the highly dense soil lecithin environment. Yeah. Because we used a pretty high concentration of liposomes. Well, it was not high enough to neglect the effect of scattering, but still it was high enough to establish the delivery process. So that's why the concentration was pretty high, around 0.02 milligrams and milliliters. So it was.
So it's not measured, but this is calculated.
It's yes. It is also for calculations.
Thank you.
Thank you.
More questions?
I have a question, Alexei. Thank you very much for the nice talk. It's got a couple of questions. One is, what are the values for viscosity did you get? I didn't see the values.
Sorry?
Values for the microviscosity.
Values for microviscosity. Well, it is here. It is nanoseconds. The thing is that if we try to calculate the microviscosity using the time-resolved anisotropy, we need to know the size of the probe. And unfortunately, the video didn't play. That's why it would demonstrate how it's difficult to estimate the size of the probe, because it can take nearly every position. But if we assume if it's small, so this, I think it can be related to 1 centipar or 5 centipars, or like 1 millipascal second, something like that.
Okay. And another question: if you add lots of molecules, do you account for homofret?
Yes. Yeah. Two typical problems that are related to home-of-threat effects. And actually most of them originated not from the overlapping of the spectrum, but of the behavior of the probe itself. For some probes, for most of the lipophilic probes, at high concentration of the probe, they start to form aggregates. And for most of the probe, the concentration when they start to do that, is more than one micromole. So for us, the concentration that was not higher was one micromole, and this concentration was everywhere the same. Not much, not more. On the other hand, we have to increase the exposition to collect more signal. And maybe nanomole concentration would be better from the point of view. But, well, 1 micromole, not much, not more. Because otherwise the effect of decreasing in average lifetime that originated from home-of-threat, not from the interaction between the carotenoids and the probe, but from there will be more significant. And you can see it's twice. It's not monotonous. It's really rapid. Not like that, like here.
More questions? If no, let's thank the speaker again.
Thank you very much.
So, next speaker is Polina Yermakova from Privolsky Research Medical University with the talk contrast-free film diagnostics of the quality of pancreas islet of Langerhans. Please.
Good afternoon. Today I want to show the presentation about contrast-free diagnostic of the quality of pancreas of Langerhans. And firstly, why it need? It is need to treat the insulin-deficient conditions. This condition develops due to disease of exocrine or endocrine part of tissue. But not only this disease is dangerous. This disease can lead to the chronic complications such as nephropathy, renopathy, and so on. So the quality of life patients is significantly reduced. The main way of treating it is insulin therapy. But even the most modern way, closed-loop system to insulin delivery don't give us the full glycemic control. So transplantation of islets is an alternative method. It's not invasive, and natural islets are much more reliable than any artificial system. So it is very important to know the quality of islets in a native tissue before islet isolation, and after that before the transplantation. Islet quality depends on their metabolism. In healthy islets, glucose stimulations leads to increase the insulin production, and it leads to increase the cell requirements of energy, and it leads to increase the mitochondrial respiration. Hyperglycemia, exocrine tissue disease, tumor, and so on leads to islet stress and increase the glycolysis. Usual modern method like PCR, immunohistochemistry, cytochemistry, and so on, don't give a complete picture of islets in native tissue and isolated islets, and they are quite contradictory. But FLIM imaging based on NNDPH is suitable to assess quality of islets in the whole tissue and in isolated way. It's not invasive and not contrast. So our aim is evaluation of FLIM possibility for islets quality assessment in healthy and pathological tissue and isolated islets during the glucose stimulation. Our task is metabolic change investigation in islets in animal model with endocrine tissue pathologies, metabolic change analysis in the islets in patients with exocrine and endocrine pathologies, and metabolic change probing of islets using upon glucose stimulation. As a material, we use samples of pancreas, rats and pigs, healthy and with diabetes as first time. We induct it by streptozotocin. In this way, we study damaged islets. And we use healthy patients' samples and samples from patients with adenocarcinoma, pancreatitis, diabetes as first time, and pancreatitis to study FLIM as a method for accessible quality of islets. We transported our samples in a special solution and called ischemia no more than an hour. FLIM imaging we made in LSM system. We calculate fluorescence lifetime and fluorescence lifetime contribution, but the A1, A2 parameters was chosen by the main parameter. Also, we study the islets in a tissue by immunohistochemistry and histological analysis. They investigate ratio of alpha-beta cell in islets by immunohistochemistry, and by histology we study the structure of islets and surrounding tissue. To study the isolation islets, we isolate them by usually method with minor modification. After that, we confirm the bioning of the islet cell, bioning to the isolated cell to the islands by Dutizon staining. We confirm their reliability by live death staining, and for metabolic study we use FLIM imaging, and to do it we incubate our islets in different glucose solution. So as a result, firstly, in results of animals, we confirm the diabetes as first type, and the islets is really was damaged because the ratio of beta cell was significantly reduced. We confirmed what islets of diabetes rat was more glycolysis, because the ratio of A1, A2 was increases. After that, we use PICS model, and our results was absolutely similar. The islets of abnormal islets was more glycolysis, and normal islets was more mitochondrial respiration way of metabolism. Bioimmunohistochemistry of islets in a patient, we see what ratio of alpha and beta cells doesn't change in pathology and in normal pancreas, but abnormal islets are smaller than normal, and it's very important that patient with diabetes of first type and pancreatitis have islets different shape from normal. Film imaging show that only one samples was different from the normal. It was the samples with from patient with diabetes and pancreatitis. So in these samples, islets was damaged not only by diseases of exocrine tissue, but also with hyperglycemia, and these samples was differ in the in greatest way, and the other samples are suitable to islet transplantation. For study isolated islets, we confirm the bioning islets, 2 islets, and their availability, and we confirm that mitochondrial respiration increase in islets due to glucose stimulation. So the FLIM method it is suitable to access islets in whole pancreas and in isolated islets. As a condition, I want to say that FLIM detect metabolic change in healthy and pathology islet cell. FLIM allow detection of changes in the metabolic status of islet cell upon glucose stimulation, and FLIM provides a non-invasive and contrast-free approach to assess the quality of islets in both whole pancreas tissue and isolated cell. So thank you. I want to thank my project manager and my team. This work was carried out by State Task. Thank you for your attention.
Please, questions? We are open for discussion.
Thank you for the talk. In your previous slide, you have mentioned the glucose stimulation using 3 micromolar and 16 micromolar. In that image, the error bar is next one. In this, no. Before the conclusion. In this image, the error bar is little bit high. So how the statistics is performed here? Like how many measurements you have made?
If the A1, A2 radio is higher, the islets increase the glycolysis. If radio A1, A2 smaller, islets increase mitochondrial respiration, and it is more better and more energy get islets by mitochondrial respiration. So healthy islets has lower level A2 and A1, A2. Any questions?
Any more questions? Okay, then we thank Polina for the talk. So the next presentation comes from Svetlana Radimova. It's on film imaging of pathological liver during regeneration. Please.
Thank the committee for the opportunity to present my work devoted to film imaging of pathological liver during the regeneration. Currently, the most effective treatment for liver tumors is still liver surgery. However, in the presence of underlying diseases such as steatosis or fibrosis, there are high risk of liver failure. And why that? Because liver regeneration potential is significantly decreased in the presence of such pathology. Traditional clinical methods are not sufficiently informative and do not allow predicting function liver after resection. So it is need to develop a new approach that effective for structural and functional, for evaluation of structural and functional state of liver tissue intraoperatively, especially intraoperatively. So the methods of multiphoton microscopy is label-free, and they can provide the possibilities to evaluate the structure and function of the liver due to the non-invasiveness and high sensitivity. So, in particular, we can evaluate the structure using a multiphoton microscopy, and using second harmonic generation, we can evaluate collagen accumulation that is really important for evaluation of structure of liver tissue as a whole. And using film, we can evaluate metabolic state of liver tissue, which can be a safe and effective method for evaluation the function of liver as a whole. So, in particular, using film, they can obtain data on fluorescence lifetimes of various forms of NADH, and indirectly judge about intensity of various metabolic pathways, for example, oxidative phosphorylation or glycolysis. So, using film, we perform analysis of metabolic state of hepatocytes. Using multiphoton microscopy, we investigate the structure of liver tissue, and using second harmonic generation, we performed the analysis of collagen accumulation. And of course, we need to compare our results with traditional methods. So, to confirm induction of liver regeneration, we performed histological analysis and biochemical blood tests. And in this slide you can see the main parameters of film analysis, and the main was contributions of the free and bound form of NADH, and also we performed third form, phosphorylated form of contribution of NADPH. In this slide, you can see the roadmap of our experiments. Steatosis was induced by high-fat diet containing 60% of fat of total diet. Fibrosis was induced by intraperitoneal injection of carbon tetrachloride. And at various stages of pathology development, we induced regeneration by 70% hepatectomy as a traditional method, and monitoring was performed on 3rd and 7th day of regeneration. Let's move to our results. Morphometric analysis show that in case of steatosis, they can see gradual decrease in proliferative activity up to 12 weeks is due to lipotoxicity and hepatocyte damage. In case of fibrosis, they can see that at the early stages of pathology, there sharp decrease in the proliferative activity, followed by increase at the later stages. That's why this because compensatory processes occurs such as regenerative nodes that is specific for such pathology. In this picture, you can see the results of histological traditional analysis, and you can see gradual increase. It's for liver with steatosis. Gradual increase of lipid infiltration and slow increase in fibrosis and collagen accumulation. And also biochemical blood tests show tissue damage and violation in synthetic function of the liver. So, we presented, here present results of our multi-photon microscopy analysis, and as you can see, in contrast with normal tissue with steatosis at the different stages of the regeneration, you can see zones with low NADH autofluorescence signal, which were associated with damaged hepatocytes and lipid infiltration in hepatocytes. Also, second harmonic generation results will consist with histological analysis, and we can see a slight increase in fibrous accumulation with a few foci of fibrosis tissue. In cases of fibrosis with induced regeneration, we also performed histological analysis which revealed at the later stages extensive fibrous tissues with multiple septa, and biochemical blood test also revealed tissue damage and violation in liver function. And we confirmed our results using multi-photon microscopy. And again, you can see that in contrast with normal tissue, we can see zones with reduced NADH autofluorescence signal, which, unlike steatosis, were associated with fibrous tissue, not with lipid infiltration. And second harmonic generation results thus consist with histological analysis, and you can see extensive fibrosis with multiple septa. In this slide, you can see phlegm analysis of the tissue, liver tissue with steatosis and different stages of regeneration, and we revealed that contributions of bound form of NADH and NADPH were reduced significantly at the early stages of steatosis, followed by increase at the later stages. And what's important, after induction of the regeneration at the later stages, you can see that in contrast with normal regeneration, there is no jump in the values at the third day of regeneration. That's explained by insufficiently of energy consumption and in particular reduced intensity of oxidation phosphorylation, which was specific for normal regeneration, and it's necessary for normal regeneration. And in case of fibrosis, we can see the same picture, the significant reduce at the early stages with increase at the later stages, and again we not observed the increase, sharp increase in contributions of bound form of NADH on third day of regeneration. But this tendency specific only for bound form on NADH, but not for NADPH. But you can see that at early stages, there's also no jump in the values of contribution. So, in general, we can say that criteria of reduced regeneration potential based on FLIM was absence of jump of values in contribution of NADH and NADPH bound form on third day. So this was associated with insufficiently energy consumption of pathology liver. So to summarize, what exactly we have determined. We determined new criteria, the presence of the pathology steatosis and fibrosis, it's the presence of zones with reduced NADH autofluorescence signal, the low values of the fluorescence lifetime contribution of the bound form NADH and NADPH before the induction, the regeneration, and that's the most important, the absence of sharp increase in the fluorescence lifetime contributions of the bound form NADH and NADPH in the proliferating hepatocytes, so after induction, the regeneration. And we believe that our criteria will be useful for express intraoperative assessment of the structure and functional state of the liver in the future in the clinic. You can see our group of biologists and surgeons, and this work was supported by Russian Science Foundation. Thank you for your attention.
Thank you very much. Questions, please? Then I will ask a question. You showed images of second harmonic from second harmonic generation microscopy. How did you quantify it? The second harmonic signal.
You mean it was not quantification, more visualization. I mean, our aim was to confirm the presence of the collagen fiber, because it's a known fact that it's specific for fibrosis. So our aim was to develop fast evaluation that will can be applied, заменить histological analysis.
So did you count the fibers or what?
What?
Did you count the fibers or what?
No, we visualize the picture. As you can see, there was a typical structure of fibers. I mean, multiple septs surrounding the tissue, regenerative nodes. It's the typical histological patterns.
Mm-hmm. Okay. Okay. Questions? Then I think we thank the speaker here. And I believe with this talk we finalize this session, and we wish you all nice evening. Thank you.
See you tomorrow.
See you tomorrow.
Let's thank our technical assistance team who made this possible. Постараюсь, да.